Hello there, and welcome to Physics with William, where curiosity gets comfortable, science speaks softly, and the universe is allowed to take its time. Tonight, we are drifting toward one of those questions that sounds simple when you first hear it, and then becomes stranger the longer you sit with it. Why is space so cold when stars are so hot? It is a fair question. In fact, it is one of those questions that feels almost too obvious to ask, which is usually where the best questions hide. When we look up at the night sky, we are looking towards stars that are unimaginably hot. Our own sun is hot enough to warm oceans, stir winds, grow forests, and turn a winter morning into something a little more forgiving. Every second it pours out light and heat in every direction. Beyond it, the galaxy is filled with other stars, some smaller and cooler, others enormous and violent, burning with temperatures that would make metal boil and rock glow like candle wax. So why does the space between them remain so deeply cold? It almost feels like a cosmic contradiction. The universe is full of furnaces, and yet the room is freezing. It is as if someone has lit billions of fires across an endless landscape, but the air between them never warms. You can imagine standing beside a campfire on a cold night. The flames crackle, the wood glows, and if you hold your hands close enough you feel the heat on your skin. Now, imagine moving away from that fire. A few steps back, the warmth fades. A little farther, the night takes over. The fire is still hot, but the world around you is not. Space is a little like that, except the campfire is a star. The night is almost perfectly empty, and the distance between one warm place and another is so large that our everyday sense of heat begins to fail us. Before we wander into the science, I want you to settle in for a moment. Wherever you're listening from, maybe it is late evening, maybe early morning, maybe you're lying under a blanket, sitting by a window, or letting this play quietly while the day loosens its grip. What is the temperature like where you are right now? Is the room warm enough? Is there a little chill at your feet? Are you listening from a city with glowing streets, a quiet countryside, a rainy apartment, or somewhere where the stars are hidden behind clouds? It is a fitting thing to notice because tonight we're talking about warmth, cold, light, darkness, and the strange fact that even a universe full of fire can feel like a freezer. And if this kind of quiet scientific wandering helps you unwind, if you enjoy letting big questions become gentle company at the end of the day, then a like or a subscription would be warmly appreciated. It helps this calm little corner of the internet reach others who may also want to fall asleep with their mind resting somewhere between a soft pillow and a distant star. No pressure, of course. The universe itself has been expanding for a very long time without rushing anyone, so we can keep the same spirit here. Now let us begin carefully, because the question is not only about stars, and it is not only about space. It is also about what heat really is. We often use heat and temperature as if they are the same thing. We say the room is hot, the soup is hot, the pavement is hot, the tea is too hot, and now we regret our confidence. In everyday life, that works well enough, but space does not behave like a kitchen, a living room, or a summer afternoon. Space is not filled with thick air that can carry warmth from one place to another. It does not have walls to hold heat in. It does not have weather in the way Earth does. There is no breeze moving warmth from a sunny patch to a shaded one. There is no blanket of air spreading heat around until everything becomes more or less comfortable. On Earth, warmth travels through stuff. That sounds simple, but it matters enormously. When you stand in a warm room, you are surrounded by air molecules. They are tiny particles, far too small to see, but there are astonishing numbers of them bumping into your skin, your clothes, the walls, the furniture, and each other. When the air is warm, those particles are moving more energetically. They collide with you and transfer some of that energy into your body. That is one reason a warm room feels warm. Heat is not just floating around as a vague feeling. It is being carried and shared by matter. The same thing happens when you touch a hot mug. Energy moves from the mug into your hand through direct contact. The particles in the mug are vibrating and jostling, and that motion is passed into your skin. When you step into a hot bath, water presses against you from all sides, and because water is much denser than air, it transfers heat very effectively. That is why bath water that is only moderately hot can feel much more intense than air at the same temperature. Matter matters. The amount of stuff around you changes how heat is felt, moved, stored, and shared. Space is different because space is mostly empty. Not completely empty, but empty enough that it makes any earthly room seem crowded beyond imagination. Between planets, between stars, and especially between galaxies, matter becomes so thinly spread that particles may travel huge distances before meeting another particle. There is almost no air. There is almost no material. There is almost nothing to bump into anything else. This means that heat cannot spread through space the way it spreads through a room. A star can be fiercely hot, but if there is not much matter nearby to absorb and carry that energy, the surrounding emptiness does not become warm in the familiar sense. That is the first important idea. A hot object does not automatically make all empty space around it hot. Heat needs a way to travel, and in ordinary life it often travels through matter. Without matter, one of the main paths for spreading warmth disappears. A star shines, yes, it releases light, and that light can cross space. But the empty space itself does not soak up heat the way a wall, a rock, an ocean, or a blanket of air would. It simply lets most of the light pass through. This can feel odd because we think of sunlight as warmth. On Earth, sunlight touches the ground, the oceans, the roofs of houses, the leaves of trees, the skin on our arms. Those things absorb the light and warm up. Then they warm the air around them. The air circulates. The planet responds. So sunlight becomes weather, climate, summer afternoons, and the smell of warm pavement after rain. But out in space, away from planets and dust and gas clouds, sunlight may travel through emptiness without warming much at all. It is not that the light is weak near a star. Close to a star it can be dangerously powerful. It is that empty space is not a substance waiting to be heated. Think of a flashlight shining across a dark room. The beam is visible if dust is floating in the air or if it lands on a wall. But if the air were perfectly clean and there were no wall, no smoke, no surface, and no particles to scatter the light, the beam would pass through without making much of itself known. Space is similar. Starlight streams across it, but unless it strikes something, a planet, a moon, a spacecraft, a grain of dust, a cloud of gas, there may be very little to receive that energy. Light is crossing the darkness, but the darkness is not warming like a blanket. This is why a spacecraft near Earth can face two opposite problems at once. One side may be exposed to direct sunlight and become very hot, while the shaded side may become extremely cold. There is no thick atmosphere around the spacecraft to even out the temperature. On Earth, if one side of a car is in sunlight, heat can still spread through the metal, the air inside, and the surrounding environment. In space, the difference between sunlit and shadowed regions can become severe. You can be burned by sunlight and frozen by shadow, not because space is behaving unfairly, but because there is so little matter to smooth the difference out. That is one of the strange things about space. It is not simply cold in the way a winter field is cold. A winter field still has air. It still has wind, moisture, ground, and clouds. It still has matter pressing against matter, sharing energy in all directions. Space cold is more like absence. It is the lack of surrounding material that can hand warmth back to you. If you are in the shade in deep space, you can radiate your own heat away, but there is almost nothing around you to return that warmth. You're not sitting in cold air. You're losing energy into a vast emptiness. This brings us to a quiet but important distinction. Temperature describes the energy of particles in a substance. But if there are almost no particles, then saying space has a temperature becomes tricky. A region of space might contain a few particles moving very fast, and in one sense those particles can be considered very hot. But because there are so few of them, they would not transfer much heat to a person or an object. This is why some parts of space can be described as having extremely high temperatures, while still being practically freezing for anything placed there. Temperature and felt heat are not always the same thing, especially when matter is spread thinly. Imagine a single mosquito flying very fast across a stadium. If you measured only the mosquito, you could say it has a lot of motion, but the stadium as a whole is not buzzing with energy. There is not enough mosquito to make the air feel crowded. In space, a few particles may be racing around with great energy, but there are so few that they cannot warm a spacecraft the way dense air or water would. Our bodies are used to environments filled with matter. Space breaks that intuition. The hot stars are real. Their energy is real. Their light is real. But cold space is also real. The two facts do not cancel each other out. They live together because the universe is not like a small room with a heater in the corner. It is more like a nearly empty ocean of distance where islands of matter glow fiercely, but the emptiness between them remains thin, dark, and poor at holding heat. Our own sun shows this clearly. It is not a gentle object. It is a vast sphere of plasma constantly releasing energy. Near the sun, radiation can be intense enough to destroy unprotected instruments. A spacecraft that travels too close needs careful shielding, and even then it must be designed with extraordinary precision. Yet the space around the sun is still a vacuum. The sunlight is powerful, but the surrounding emptiness is not like hot air. If you are directly exposed, you absorb energy and heat up. If you are shielded, you can cool rapidly by radiating energy away. The same region can feel burning or freezing depending on whether light is reaching you and whether you have a way to keep your own heat. This is why astronauts wear suits that are not simply winter coats. A spacesuit is not just insulation against cold. It is a small life support system, a personal environment, a controlled bubble of pressure, oxygen, cooling, heating, and protection. In sunlight, an astronaut can absorb too much heat. In shadow, they can lose too much heat. The suit must manage both. It has to protect against the harshness of light and the emptiness of darkness. That is a much stranger challenge than simply staying warm on a snowy walk. The more we look at the question, the more it becomes a lesson in how different the universe is from the places where our instincts were made. Human intuition grew up inside an atmosphere. Every breath we take depends on a thick mixture of gases held close by gravity. We live on a planet where heat moves through air, water, stone, soil, skin, and cloud. When something hot burns nearby, the air warms and moves. When the sun rises, the ground absorbs light, the air responds, and we call it morning. So when we imagine stars scattered through space, it is natural to assume their heat should fill the space around them. But space does not behave like air. Space is not a pot of soup being warmed from many sides. It is not a house with radiators. It is not a cave with torches on the wall. It is mostly emptiness, and emptiness is bad at becoming warm. You can fill emptiness with light, but unless that light is absorbed, it remains on the move. Starlight can travel for years, centuries, or far longer, crossing immense distances until it meets matter. A tiny fraction enters your eyes when you look up at night. Other light lands on planets, comets, dust grains, and telescopes. Much of it simply keeps going. There is also the matter of distance. Stars are hot, but they are very far apart. Our sun feels dominant because we're close to it by cosmic standards. It fills our sky with daylight because Earth orbits nearby. But the next nearest stars are so far away that their light arrives as faint points in the night. They may be powerful, but distance spreads their energy thin. A candle across a room can be seen, but it will not warm your hands. A star across many light years can shine in your sky, but its heat is not arriving in a way that changes your room, your skin, or the space around Earth. The universe contains many stars, but it also contains enormous distances between them, and distance weakens the warming effect of each one. This is part of the answer to a related puzzle. If the universe has so many stars, why is the night sky dark? Why does every direction not end at the surface of a star, filling the sky with light? The answer involves the age of the universe, its expansion, the finite speed of light, and the fact that not all starlight has had time to reach us. It is a beautiful question in its own right, and it connects to tonight's subject because darkness and cold often travel together in our imagination. But space is not cold merely because it is dark, and it is not dark merely because it is cold. Both facts arise from the structure and history of the universe, from distance, expansion, matter, radiation, and time. Even the background glow of the universe has cooled. Long ago, the universe was much hotter and denser than it is today. As it expanded, the radiation left over from that early state stretched and cooled, until it became a faint microwave glow spread across the sky. This background radiation gives deep space a very low baseline temperature. It is not absolute nothingness. The universe still has a faint afterglow, a relic warmth from its earliest history. But by any human standard, it is profoundly cold. It is the cooled whisper of a once blazing universe, now stretched across cosmic distances. That idea can feel almost comforting. Space is cold not because the universe lacks heat, but because heat has history. Energy moves, spreads, dilutes, escapes, and changes form. Stars gather matter into bright centres where energy is produced and released. Planets catch a little of that energy and become places where weather, oceans, and perhaps living things can exist. Between those places, the universe is mostly open, sparse, and quiet. It does not hold warmth easily. It lets light pass. It lets heat escape. It gives every glowing object room to shine without turning all of reality into a furnace. So the question becomes less of a contradiction and more of a doorway. Why is space so cold when stars are so hot? Because heat is not just about hot things existing. It is about matter, contact, radiation, distance, absorption, and balance. It is about whether energy has somewhere to go and something to warm when it gets there. Stars are hot because they are dense, energetic, and filled with matter in motion. Space is cold because it is thin, vast, and mostly empty. The stars burn inside the universe, but they do not make the whole universe feel like the inside of a star. And that is where our gentle journey begins, not with the stars themselves, but with the word cold. Because before we can understand why space is cold, we have to understand what cold really means, when there is almost nothing there to be cold in the first place. That is where the word cold starts to misbehave. On Earth, cold usually feels like a clear and simple thing. You step outside on a winter morning, the air touches your face, your fingers stiffen a little, and your body immediately understands the situation. Cold means the air is taking warmth from you faster than your body would like. Cold means your skin is losing energy. Cold means your breath becomes visible, the pavement looks pale, and the kettle suddenly becomes the most important machine in the house. But space does not offer cold in that familiar way. Space is not a winter morning. It is not a freezer. It is not a room where someone forgot to close the window. It is much stranger than that, because in ordinary life, cold is something we feel through contact with matter, and space has almost no matter to make contact with us. There is no thick air pressing against your skin. There is no wind to carry heat away. There is no cold ground under your feet. There is no surrounding atmosphere politely taking part in the exchange. There is mostly emptiness, and emptiness changes the meaning of cold. This is the first reason the cold of space is not quite like any cold we experience naturally on Earth. When people imagine floating in space, they often picture a person instantly freezing solid, almost like a glass of water placed in the back of a freezer. It is an understandable image. Space is often described as extremely cold, and when we hear extremely cold, our minds reach for the coldest things we know. Ice, snow, frozen lakes, metal railings in January. or that one corner of the house that never seems to warm up no matter how hard the heating system tries. But freezing in space would not happen in the same way freezing happens in air or water. The situation is far more complicated, and in some ways, far less dramatic than the movies suggest. On Earth, when something cools down, it usually loses heat through contact. Put a warm spoon into a bowl of ice cream, and energy leaves the spoon and enters the ice cream. Put your hand on a cold window, and warmth moves from your skin into the glass. Stand in a cold wind, and moving air sweeps heat from your body. Fall into cold water, and water steals heat far faster than air because it is dense and presses against you everywhere at once. These are all ways matter moves energy around. The more matter there is, and the better that matter is at carrying heat, the faster warmth can leave. Space removes most of that contact. If you placed an object in deep space, away from sunlight, it would cool mainly by giving off radiation. Radiation is energy carried by light, including forms of a light our eyes cannot see. Every warm object gives off this kind of energy. A person does it. A planet does it. A cup of tea does it, though the cup of tea is usually more useful in a conversation. When an object radiates energy into space, that energy can travel away. If the object is not receiving enough energy back from sunlight, starlight, or nearby warm surfaces, it cools. But because space has so little matter, there is no surrounding cold air to rush in and pull heat away quickly. This means an object in shade does not necessarily freeze instantly. It loses heat steadily through radiation, but the pace depends on what it is made of, how warm it is, how reflective it is, how much surface area it has, and whether anything nearby is shining on it. Space can be a very effective place for cooling over time, yet not because it is full of cold stuff. It is effective because it gives heat a vast place to escape to, and very little comes back. That is a subtle difference, but an important one. A freezer cools you because cold air or cold surfaces are in contact with you. Space cools you because in darkness, you radiate energy away into emptiness. On Earth, cold often feels like an attack from the outside. In space, cold is often more like an unanswered farewell. Your warmth leaves, and the universe does not return much of it. This also explains why space can be both freezing and scorching, depending on where you are and what is shining on you. Near Earth, sunlight is strong. If you are exposed directly to it, you absorb energy and can become dangerously hot. If you're in shadow, you can lose energy and become dangerously cold. There is no comfortable air between those extremes to soften the difference. One side of an object can bake in sunlight while the other side cools in darkness. This is not because space cannot decide what temperature it wants to be. It is because space is not acting like a normal environment at all. It is not wrapping you evenly in warmth or cold. It is simply allowing energy to arrive from one direction and escape in another. A useful way to think about it is to imagine standing near a fire on a very cold night, but with one important change. Imagine there is no air around you. The fire shines on the front of your body, so that side receives heat. But the back of your body faces open darkness, and there is no warm air flowing around to share the heat. The front can become too warm while the back cools. That is not how campfires work on Earth, because air, smoke, ground, clothing, and nearby objects all help move energy around. In space, the balancing act becomes much harder. This is one reason spacecraft design is so demanding. Engineers do not simply build a strong metal shell and call it a day, they have to manage heat constantly. Spacecraft need ways to reflect sunlight, absorb heat where useful, release heat where necessary, and keep delicate instruments within safe operating ranges. Some parts of a spacecraft generate heat by working. Electronics, batteries, motors, and communication systems all produce waste heat. On Earth, a fan can blow air across a warm component. In space, there may be no air to blow. Heat must be conducted through materials inside the spacecraft and then radiated away from special surfaces. Thermal control in space is not an afterthought. It is one of the central problems of survival and operation. The oddness deepens when we talk about temperature. In everyday conversation, temperature tells us how hot or cold something is. A warm room has one temperature, a cold lake has another, but temperature is closely tied to the motion of particles in matter. Air has particles. Water has particles. Stone has particles. Your body has particles. When those particles are moving and vibrating more energetically, we say the substance has a higher temperature. When they are moving less energetically, we say it has a lower temperature. Space, however, may have so few particles that temperature becomes less useful in the familiar sense. There are places above Earth where the few particles present are moving extremely fast. Scientists may describe those regions as very hot. Yet if a human body or a spacecraft were there, those particles would not feel hot in the ordinary way, because there are too few of them to transfer much energy. It is a little like being struck by one warm grain of sand in a huge empty stadium. The grain may carry energy, but one grain cannot heat the stadium, and it cannot warm you the way a beach full of hot sand would. This is why a region of space can have a high temperature in scientific terms and still be unable to warm an object effectively. Temperature tells us about the average energy of particles, but it does not tell us how many particles are available to share that energy. Heat, in the practical sense of warming something up, depends not only on how energetic particles are, but also on how many there are and how often they collide with you. Dense warm air can heat you. Dense cold water can chill you quickly. Sparse hot particles in space may barely touch you at all. There is a part of Earth's upper atmosphere called the thermosphere, and it gives a helpful example of this difference. The few particles there can be very energetic, so the region can be described as extremely hot, but it would not feel like standing in a blast furnace. There are not enough particles to deliver that heat efficiently. An object there can still lose heat by radiation. This sounds strange until we remember that our senses were built for dense environments. We judge heat through skin, air, moisture, and contact. Space does not play by those rules. So when someone says space is cold, we have to ask what they mean. Do they mean the background radiation of the universe is very cold? Do they mean an object placed in shadow will cool down? Do they mean the matter between stars has very little thermal energy per volume because it is so thin? Do they mean there is no warm air to surround and protect you? All of these can be true in different ways, but they are not the same statement. The cold of deep space is often connected to the faint background glow left over from the early universe. This glow is everywhere, but it is now very weak. It represents a very low temperature, only a little above the coldest possible limit. If an object were placed far from stars, planets, and dust, and if it had enough time to come into balance with that background glow, it would cool to a very low temperature. That is the deep cold people often mean when they describe empty space. It is not a gust of icy wind. It is the quiet thermal state of an old expanded universe where radiation has been stretched and diluted across immense distances. But most real places in space are not perfectly isolated. A spacecraft near Earth receives sunlight, reflected light from Earth, infrared radiation from the planet, and heat from its own systems. A rock near the sun can become extremely hot. A rock in shadow can become extremely cold. A dust grain between stars may be warmed slightly by starlight and cooled by radiation. A gas cloud near young stars may be heated by ultraviolet light. Space is not one uniform freezer with a single setting. It is a set of environments where energy arrives and leaves in different ways. This is why the phrase cold space can be misleading. It makes space sound like a substance, as if the darkness itself has a temperature pressing against everything inside it. But space is not a substance in that ordinary sense. It is the arena in which matter and radiation exist. Some regions are filled with energetic radiation. Some contain thin gas. Some are almost empty. Some sit close to stars. Others lie between galaxies where even starlight is faint. Calling all of it cold is useful as a first approximation, But the details are more interesting. The human body adds another layer to the confusion. We are warm creatures. Our bodies constantly produce heat through metabolism. On Earth, we lose heat to the environment through air, water, surfaces, evaporation, and radiation. Clothing helps by trapping air near the skin, reducing heat loss. Blankets work not because they create heat by magic, though on a tired evening they can feel suspiciously magical, but because they slow the escape of heat and keep a layer of warmer air close to us. In space, a blanket alone would not solve the problem. It might slow radiation, but there is no breathable pressure, no oxygen, and no normal atmosphere. A human without protection would face many dangers long before the simple idea of freezing became the main issue. The absence of pressure would be severe. The lack of oxygen would be immediate. Moisture exposed to vacuum would behave in dangerous ways. The body would not explode, despite some old science fiction habits, but the situation would be rapidly life-threatening. Temperature would matter, but it would not be the only danger, or even the first one in the way people often imagine. The more accurate picture is that space is thermally unforgiving. It does not help you regulate. It does not provide air to breathe or carry heat evenly. It does not cushion you from sunlight or shade. It does not politely keep everything at a comfortable average. It leaves objects to balance incoming radiation, outgoing radiation, and their own internal heat. That balance can lead to very high temperatures in one place and very low temperatures in another. Consider the moon. It has no thick atmosphere to spread heat around. During lunar daytime, the surface can become hotter than boiling water. During lunar night, it can fall to temperatures far below any winter on Earth. The same world can swing between extremes because there is no atmosphere to moderate the heating and cooling. The moon is not far from the sun compared with Earth. It receives the same general sunlight that Earth does. But without oceans and air, the warmth does not circulate in a familiar way. The surface bakes when lit and chills when dark. Earth, by contrast, is protected by its atmosphere and oceans. The atmosphere absorbs, scatters, and redistributes energy. Winds move warmth from one region to another. Clouds reflect sunlight and trap some outgoing heat. Oceans store huge amounts of energy and release it slowly. Night does not instantly freeze the surface because the ground, air, and water hold heat and share it. Weather may be messy, but it is also a thermal smoothing system. It keeps Earth from behaving like a bare rock in space. That is one of the hidden gifts of living here. We do not merely receive sunlight. We live inside a planetary system that catches that sunlight, stores some of it, moves it around, and releases it gradually. Our sense of normal temperature comes from that complex balance. Space strips most of that away. Without air and water, heat becomes less communal. Sunlit surfaces and shadowed surfaces go their separate ways. This is also why the coldness of space does not contradict the heat of stars. A star is a dense object where matter is packed together and energy is produced in its core. The particles inside a star are constantly interacting, colliding, transferring energy, and emitting radiation. It is a place where heat has plenty of matter to work with. Empty space is the opposite. It has little matter, few collisions, and enormous distances. A star can shine through space, but the emptiness does not become a warm atmosphere around it. The word "through" is important. Light travels through space very well, precisely because space is so empty. If space were filled with thick gas, starlight would be absorbed and scattered much more strongly. The night sky would look different. Stars might warm the material between them more effectively, but their light might not travel as freely. The universe we see is visible to us partly because space is transparent. It lets light cross great distances. The same emptiness that makes space cold also allows stars to be seen. There is a quiet trade there. Space does not hold warmth well, but it carries light beautifully. It is cold because it is empty, and it is clear because it is empty. The darkness between stars is not a wall. It is a vast openness through which ancient light can move. When you look at a star, you're not seeing heat stored in the space between you and it. You're receiving a small stream of radiation that has crossed that space without needing the space itself to warm up. This helps explain why looking at the night sky feels so different from standing in sunlight. At night, you may see many stars, but their combined light is extremely weak compared with the sun. They're far away. The radiation reaches Earth as tiny amounts of energy. Your eyes are sensitive enough to detect them, especially after adapting to darkness, but your skin is not warmed by them in any noticeable way. Seeing is not the same as being heated. A distant star can be visible without being thermally important to your body. Our intuition often mixes brightness and warmth because the sun gives us both. Daylight is bright and warm, fire is bright and warm, a glowing stove is bright and warm, but in astronomy, light can be bright to an instrument and still carry little warming power by the time it arrives. A telescope can collect faint photons from a galaxy billions of light years away, but that galaxy is not heating the telescope in any everyday sense. Detection is not the same as comfort. The deeper lesson is that cold is not just a number. It is a relationship between an object and its surroundings. A thing feels cold to you if it pulls energy from your body. A place is dangerous thermally if it causes your body or machinery to gain or lose energy faster than can be managed. Space is strange because the surroundings are often not surrounding you in the usual way. They are too thin, too empty, too directional. Sunlight may come from one side, darkness waits on the other. Your own heat leaves in all directions. Matter is scarce. Balance becomes fragile. This is why the question has such a satisfying twist. Space is cold not because stars fail to be hot, but because hot stars and cold space are parts of the same cosmic arrangement. Stars are concentrated places where matter and energy gather. Space is the vast separation between those concentrations. The universe is not evenly warmed because matter is not evenly spread, radiation is not evenly absorbed, and distance is enormous. Fire can exist in a cold universe if the fire is isolated and the space around it is mostly empty. And once that becomes clear, the cold of space stops being just a dramatic fact and becomes a clue. It tells us that heat is not a simple substance leaking out of stars like steam from a kettle. It tells us that warmth requires exchange. It tells us that matter changes everything. It tells us that the universe can contain extremes side by side because there is no universal air to smooth them out. A star can be violently hot. A shadow nearby can be bitterly cold. A particle can be energetic. A region can still feel empty. A spacecraft can need protection from overheating and freezing during the same journey. So the next time the phrase cold space comes to mind, it may help to picture not an icy wind, but a lack of touch. No air pressing warmth back against you. No walls glowing gently around you. No atmosphere spreading heat from day into night. Just radiation arriving, radiation leaving, and matter trying to keep its balance in a place that gives it almost nothing to lean on. From there, the next step is to separate two ideas that everyday language tends to blend together. One is heat, the actual transfer of energy from one thing to another. The other is temperature, the measure of how energetic the particles in something are. On Earth, they usually travel together closely enough that we forget they're different. In space, the difference becomes impossible to ignore, and it begins to explain how something can be scientifically hot, practically cold, and deeply confusing all at once. The easiest way to get lost in this question is to treat heat and temperature as if they are two names for the same thing. In ordinary life, we can usually get away with that. A hot stove has a high temperature, and it can burn your hand. A cold drink has a low temperature, and it can cool you down. A summer pavement is hot, a winter window is cold, and no one needs a lecture in thermodynamics before deciding whether to wear socks. Everyday language works because everyday environments are dense, familiar, and full of matter. Air surrounds us, water touches us, ground supports us. objects press against objects. Heat has many convenient ways to move around. Space takes away that convenience. Once we leave Earth, heat and temperature begin to separate in ways that feel strange at first. A place can contain particles with very high temperature and still not warm you very much. Another place can have a very low background temperature, but if sunlight is shining on you, you may overheat. A thin gas can be technically hot while carrying very little total heat. A dense object at a moderate temperature can be far more dangerous to touch than a nearly empty region whose few particles are moving extremely fast. This is not wordplay. It is one of the key ideas needed to understand why space can be cold, even though stars are hot. Temperature is about the average motion of particles in matter. When particles are moving, vibrating, rotating, or jostling more energetically, we describe the material as having a higher temperature. When that motion is less energetic, the temperature is lower. This is true for solids, liquids, gases, and plasmas, though each behaves in its own way. In a metal spoon, atoms vibrate in place. In a glass of water, molecules slide and tumble around each other. In air, molecules fly about and collide. In the hot plasma of a star, charged particles move violently in a dense glowing storm. Temperature is a way of describing the average energy of those microscopic motions. Heat is different. Heat is energy moving from one thing to another because of a temperature difference. It is not just the fact that particles are energetic, it is the transfer of energy. Heat is what passes from a hot mug into your fingers, from your body into cold air, from sunlight into the surface of a planet, from a warm engine into the surrounding environment. Temperature tells us something about how energetic the particles are. Heat tells us about energy being exchanged. That difference may sound small, but it becomes enormous in space. Imagine a crowded room full of people all moving around. If the room is packed, people constantly bump into each other. Motion spreads quickly through the crowd. Now imagine a huge, empty hall with only 3 people sprinting across it. Each runner may be moving very fast, but because there are so few people, the hall as a whole does not feel crowded or energetic. If you stood there, you might never be touched at all. The runners have plenty of motion individually, but there is not much total interaction. A thin gas in space can be like that enormous hall. The individual particles may be moving extremely fast, so scientists can describe the gas as having a high temperature. But there are so few particles in each volume of space that the gas contains very little total thermal energy compared with something dense. It cannot deliver heat efficiently to a spacecraft or a person because it rarely collides with them. A dense object at a lower temperature can transfer far more heat because it has many more particles making contact. This is why the temperature of a thing does not automatically tell you how much heat it can give you. A spark from a fire may be extremely hot, but it is tiny. It can sting your skin, but it does not warm your whole body. A bathtub filled with warm water may have a much lower temperature than that spark, but it contains far more total thermal energy because there is so much water. Sit in it, and it can warm you for a long time. The spark is hotter by temperature. The bath holds more heat in the practical sense that matters to your body. The same idea explains why a baking tray from an oven can burn you more seriously than a bit of hot air at the same temperature. Air is thin, metal is dense, and conducts energy well. Touch the tray, and many particles in the metal can pass energy into your skin quickly. Wave your hand briefly through warm air, and there are fewer particles colliding with your skin, so less energy is transferred in that moment. The temperature may be similar, but the heat transfer is very different. Water makes this even clearer. Cold air on a winter day can feel unpleasant, but cold water at the same temperature can become dangerous much faster. Water is dense, and it carries heat away from the body very efficiently. Your body loses energy into the water at a much greater rate than it would into air. That is why being soaked in cold weather is worse than being dry. It is not only the temperature that matters, it is the material touching you, how much of it there is, and how quickly it can carry energy away. Space has almost none of that touching material, so when we ask whether space is hot or cold, we have to be careful. If we mean the background radiation left over from the early universe, then deep space is extremely cold. If we mean the temperature of a thin cloud of charged particles above Earth, then some regions can be described as very hot. If we mean what would happen to a dark object far from stars, it would gradually radiate away its heat and become very cold. If we mean what happens to a sunlit object near Earth, it may overheat. The answer depends on whether we are talking about particle motion, energy transfer, radiation, density, or the balance between incoming and outgoing energy. This is where stars enter the story in a clearer way. A star is not just hot in the sense that its particles are energetic, it is also dense compared with space, especially in its deeper layers, and it produces enormous amounts of energy. The Sun contains a vast quantity of matter. Its interior is packed with plasma under tremendous pressure. Energy created in the core gradually works its way outward and eventually escapes as radiation from the surface. When that radiation reaches Earth, some of it is absorbed by land, ocean, air, clouds, plants, buildings, and skin. Those things warm up because they take in energy. But the empty space between the Sun and Earth does not warm up like air in a greenhouse. Most of the sunlight simply travels across it. There are too few particles in the vacuum to absorb much of the energy, so the radiation remains radiation, moving through emptiness until it strikes matter. Space does not need to be warm for sunlight to cross it. In fact, the emptiness makes that crossing easier. This is a useful mental shift. A hot star does not heat space the way a stove heats a kitchen. A stove warms the air around it, and the air spreads that warmth through the room. The Sun sends radiation through vacuum. That radiation can warm objects it hits, but it does not require the vacuum itself to become warm. The vacuum is not a thick medium. It is not a pot of water. It is not a blanket of air. It is mostly an absence of matter, and absence does not store heat well. Temperature also depends on what is being measured. If you put a thermometer in a room, air molecules collide with it over and over until the thermometer settles to the temperature of the air. There are enough collisions for the thermometer to come into balance with its surroundings. In deep space, a normal thermometer would not work in the same straightforward way. There may not be enough particles around to collide with it and set its temperature. Instead, the thermometer would be affected mainly by radiation. Is it in sunlight or shadow? Is it near a planet giving off infrared radiation? Is it facing cold, deep space? What is it made of? How well does it absorb and emit radiation? The reading would tell you about the object itself and its energy balance, not simply the temperature of some surrounding air, because there is no surrounding air in the ordinary sense. This is why spacecraft are designed with surfaces that carefully control how they absorb and emit radiation. Some materials are shiny to reflect sunlight. Some are dark to radiate heat away. Some parts are wrapped in multi-layer insulation that looks a little like delicate metallic foil. These layers reduce unwanted heat transfer by radiation. The spacecraft is not trying to stay warm in cold air. It is trying to manage energy in a place where radiation is the main conversation with the outside world. A person in space would face the same basic issue, though with much higher stakes. Your body produces heat all the time. On Earth, you lose it through air, sweat, contact with surfaces and radiation. In space, without a suit, the lack of pressure and oxygen would be immediate dangers, but thermally speaking, your body would not be surrounded by cold air pulling heat away. It would radiate heat into space. If sunlight struck you, you would also absorb energy. The result would depend on exposure, shadow, and time. The common image of instant freezing is misleading because it assumes space behaves like a very cold fluid. It does not. There is no icy air rushing over you. There is almost nothing there. The difference between heat and temperature also helps explain why astronauts can work in orbit, while Earth shines below them and the sun blazes nearby. Their suits and spacecraft do not simply protect them from cold, they protect them from imbalance. Too much incoming radiation can cause overheating. Too much outgoing radiation without enough replacement can cause cooling. Electronics inside a spacecraft generate heat that must be removed. Human bodies generate heat that must be controlled. A sealed cabin can get too warm if waste heat has nowhere to go. In a vacuum, getting rid of heat can be just as important as keeping it. That may sound surprising. We imagine space as cold, so we imagine the main engineering challenge must be staying warm. But for many spacecraft, removing heat is a constant concern. Computers, instruments, batteries and people all produce thermal energy. On Earth, heat can be carried away by circulating air or water. In space, engineers often guide heat through solid materials to radiators, which then release energy as infrared radiation. The spacecraft must glow away its unwanted heat, not visibly like a lamp, but in a form of light our eyes cannot see. It is a slow, carefully planned process. This is why the vacuum of space is sometimes a good insulator. A vacuum flask, often used to keep drinks hot or cold, relies on this principle. By removing most of the air between its inner and outer walls, it greatly reduces heat transfer by conduction and convection. Your hot drink stays hot longer because there are fewer particles available to carry energy away. Your cold drink stays cold because there are fewer particles carrying heat in. Space is the grand version of that absence, though radiation still remains. A vacuum reduces some kinds of heat transfer, but it cannot stop light from carrying energy. There are three main ways heat moves in ordinary life, and space changes all of them. Heat can move by direct contact through materials. This is conduction. Heat can move through the motion of fluids like air and water. This is convection. Heat can move as radiation carried by light. In space, conduction only matters where objects touch. Convection needs a fluid, so in empty space it is mostly absent. Radiation becomes the dominant method for energy exchange over distances. That is why sunlight can cross the vacuum and warm Earth, and why a dark object can cool by radiating its energy away. No formulas are needed to see the importance of this. Think of 3 cups of tea. One sits on a metal table, one sits in a drafty room, and one floats in a vacuum chamber. The tea on the metal table loses heat through contact with the table. The tea in the drafty room loses heat as air moves over it and carries warmth away. The tea in the vacuum chamber cannot lose much heat by air motion because there is almost no air. It still radiates energy, but the cooling process is different. Space is not the drafty room. It is closer to the vacuum chamber, except with sunlight, shadow, and cosmic background radiation added to the story. Temperature without density can deceive us. Heat transfer without contact can be slow or directional. Radiation can be powerful if there is a nearby star, faint if there is not, and unavoidable because every warm object emits it. These are the pieces that make space feel so unlike Earth. We're used to environments where heat is shared through matter constantly. We walk through air without thinking about the billions upon billions of collisions happening around us. We sit in rooms where walls, floors, furniture, and bodies exchange energy. We live inside a thick planetary blanket. Space removes the blanket. That removal makes temperature less immediate. A region can be called hot because of the speed of its few particles, but it may not heat anything effectively. A region can be called cold because the radiation background is extremely weak, but sunlight can still make an exposed surface dangerously hot. An object can be cold on one side and hot on the other because there is no atmosphere to even things out. A spacecraft can need heaters and radiators at the same time. None of this is contradiction. It is the natural result of separating temperature from heat and heat from the dense environments we know. Even on Earth, we already have small hints that temperature alone is not the whole story. A wooden bench and a metal bench in the same room are at the same temperature, but the metal feels colder because it conducts heat away from your skin more quickly. A dry sauna can have air at a temperature that would seem alarming, but because air is not very dense and sweat can evaporate, you may tolerate it for a short time. Put your hand in water at a much lower temperature, and it may feel far more intense because water transfers heat efficiently. Our senses do not measure temperature directly. They respond to heat flow. They tell us how quickly energy is leaving or entering the body. That is why cold is partly a biological experience. Your skin senses changes in heat flow. If energy leaves your skin rapidly, you feel cold. If energy enters rapidly, you feel hot. In space, without air pressing against you, those familiar cues would be absent or distorted. You would not feel a cold wind. You would not feel cold water. You would not feel a winter surface unless you touched one. Instead, your thermal state would depend on radiation, internal heat, and any materials in contact with you. Space cold is not a sensation of being surrounded by icy matter. It is the vulnerability of radiating into a vast sink with little warmth returning from the dark. A star, meanwhile, is a place where temperature and heat are both enormous. The particles are energetic and there is a tremendous amount of matter involved. Energy is produced and transported outward. Radiation pours away in all directions, but as that radiation spreads, it becomes less concentrated with distance. A planet close enough can absorb enough of it to warm. A dust grain can be heated. A telescope mirror can warm if exposed. But the vacuum between does not become a warm bath. It remains mostly transparent, mostly empty, and poor at storing the energy passing through it. This is one reason life on Earth depends not only on the sun, but on Earth being the kind of object that can catch sunlight and make use of it. The ground absorbs, the oceans store, the atmosphere redistributes. Greenhouse gases slow some of the outgoing infrared radiation. Clouds reflect and trap. Winds carry, currents circulate. The planet turns sunlight into climate because it is made of matter arranged in a complex system. Without that system, sunlight alone would not create the gentle range of conditions we know. The moon receives sunlight too, but without a thick atmosphere and oceans, its surface temperatures swing wildly. Same star, different thermal story. The lesson is simple, but it changes everything. Temperature is not the same as heat. Heat is not the same as warmth felt by a body. Warmth requires energy transfer, and energy transfer depends on matter, radiation, contact, density, distance, and time. Space forces these ideas apart. It reveals that our everyday language has been quietly relying on Earth's atmosphere all along. Once that distinction is in place, the original question becomes less puzzling and more precise. Stars are hot because their matter is energetic and dense enough to produce and release vast amounts of energy. Space is cold because it contains so little matter, absorbs so little of that radiation, and gives objects few ways to receive warmth unless they are directly exposed to light. A hot star can shine across a cold vacuum because the radiation travels through emptiness rather than heating it like air. And with that difference settled, the next piece comes into view more naturally. If stars are not warming space the way a campfire warms the air around it, then we need to look more closely at why the campfire comparison fails. A fire on Earth warms you through flames, hot gases, glowing embers, heated air, and nearby surfaces. A star warms across space mostly by radiation alone, and that single fact changes the entire feeling of the universe. A campfire teaches us many useful things about heat, but it also teaches us a few habits that stop working once we leave Earth. If you sit near a fire on a cold evening, the warmth seems to spread out from the flames into the space around them. Your hands warm up, your face warms up. The air close to the fire feels different from the air behind you. Smoke rises, sparks lift, and the whole scene gives the impression that heat is something that pours outward and fills the nearby surroundings. That impression is reasonable because on Earth, a fire is not just a glowing object. It is part of a thick environment. It has air to feed it, air to carry heat, ground beneath it, people around it, and countless particles moving, colliding, expanding and flowing. A campfire warms its surroundings because its surroundings are made of matter. A star is not in that kind of setting. A star shines into a vacuum. It has no thick atmosphere stretching between itself and distant planets in the ordinary sense. It has no room full of air to stir. It has no smoke drifting upward, because upward only has meaning when gravity and air give it one. It has no nearby walls to catch warmth and send it back. It releases a huge amount of energy, but most of that energy leaves as radiation, travelling through space until it hits something. The star is hot. The light is energetic. But the emptiness between the star and the next solid object is not a material that can be heated like air around a flame. That is the key difference. A campfire warms you through several paths at once. Some warmth reaches your skin as radiation, the same broad kind of process by which sunlight crosses space. You can feel this when you hold your hands toward the flames. Even if the air between you and the fire is cool, the glowing embers and flames send energy directly to your skin. But a campfire also warms the air. Hot gases rise from the flames. Cooler air flows in, and a steady circulation begins. This moving air carries energy away from the fire and spreads it through the surroundings. The stones around the fire warm up. The ground warms. Nearby objects absorb and release heat. The whole environment participates. In space, almost all of that participation disappears. There is no air to heat and circulate. There are no thick gases between most stars and planets to carry warmth by flow. There is no cozy mixing. There is mostly radiation moving in straight paths until it is absorbed or scattered. So a star does not warm space the way a fire warms a campsite. It sends energy across space, but the space itself mostly lets that energy pass through. This is why sunlight can travel from the sun to Earth without making the space between them warm in the familiar sense. The sunlight is real, and it carries enough energy to drive nearly all life on our planet. Yet the vacuum it crosses is not like a transparent oven. It does not gradually fill up with heat. It does not become a warm breeze. The radiation remains on its way until it meets matter. When it reaches Earth, it encounters atmosphere, ocean, rock, soil, ice, leaves, rooftops, and skin. Those things absorb some of the light and warm up. Then they share that warmth with the air and water around them. The warming we experience is not because space has become warm on the journey. It is because Earth catches the light. A campfire is local. Its warmth fades quickly because the fire is giving energy to the air around it, and that air is constantly moving. If the wind shifts, you feel it immediately. One moment your hands are comfortable, the next your face is full of smoke and you're wondering why you chose that exact seat. The fire heats a small region because there is plenty of matter nearby to absorb and carry the energy. A star, on the other hand, is enormously more powerful, but the distances involved are enormously larger. Its radiation spreads outward in all directions. As it spreads, the same total output is shared across a larger and larger area. By the time starlight reaches a distant planet, it may still be important, but it is far less concentrated than it was near the star. This spreading matters because warmth depends not only on how hot the source is, but also on how much of its energy reaches you. A small candle next to your hand warms you more than a huge fire on a faraway hill. The distant fire may be far hotter and more powerful overall, but only a small portion of its radiation reaches your skin. Stars work by the same principle, though on a much grander scale. Our sun dominates Earth because we're close enough to receive a strong flow of its radiation. Other stars are hot too, but they are so far away that their light arrives as tiny amounts of energy. We can see them because our eyes are sensitive, especially in darkness, but they do not warm us. The night sky can be full of hot stars and still leave the air cold. There is a useful comparison hidden in ordinary daylight. When you stand in sunlight, you feel warmth because your body absorbs some of the sun's radiation. Step into shade, and the direct radiation is blocked. The air may still be warm because Earth's atmosphere and surface have been heated. but the immediate sunlight is gone. On an airless world, that difference becomes much stronger. A sunlit surface can become extremely hot, while a shadowed surface nearby can become extremely cold. Without air to mix the temperatures, light and shadow become sharply different thermal worlds. The moon shows this clearly. The sun shines on the moon almost as it shines on Earth, but the moon has no thick atmosphere and no oceans to move heat around. During its long day, the surface in sunlight can become very hot. During its long night, the surface can become intensely cold. It is the same sun. The difference is the missing environment. Earth has air and water to soften the extremes. The moon does not. Space does not. A campfire warms a campsite partly because the campsite has air. A star lights a vacuum, and the vacuum does very little with that light. This also explains why being closer to a star does not mean the empty space around it behaves like hot air. Close to the sun, radiation is intense. A spacecraft exposed to it must be protected from overheating. But if a surface is shielded from the sun and faces deep space, it can radiate heat away and become very cold. The environment is not evenly warm, it is directional. Energy arrives from the starward side. Energy leaves toward the darkness. Objects in space must manage this imbalance carefully. They are not sitting inside a gently heated room. They are placed between a bright source and a cold sink. The word sink here simply means a place where energy can go. Deep space acts like a vast receiving background for outgoing radiation. If an object is warm, it emits infrared radiation. In a dark direction, that radiation can escape with little coming back. On Earth, the surroundings usually return some radiation. Walls, air, ground, trees, clouds, and nearby objects all emit energy too. Even on a cold night, you're surrounded by matter that exchanges radiation with you. In space, if you face away from the sun, there may be very little radiation returning from that direction. Your heat can leave, and the darkness does not send much back. A campfire is different because the environment around it traps and recirculates some energy. Hot air rises but remains part of the atmosphere. Warm ground releases heat slowly. Nearby rocks absorb energy and continue glowing faintly in infrared after the flames shrink. People around the fire block reflect and radiate heat. The whole scene is messy and connected. Space is cleaner in the scientific sense and harsher in the practical sense. Energy can simply depart. It may help to picture a star as a lamp in an enormous empty warehouse with no walls close by. The lamp is powerful, and anything placed in its beam will be illuminated and warmed. But the empty volume between the lamp and the object does not become warm unless it contains dust, gas, or surfaces that absorb the light. If the warehouse were filled with fog, the beam would scatter and the fog might warm slightly. If it were filled with air, heat could be carried around. If it had walls nearby, the walls would absorb and return energy. Remove almost everything, and the lamp can shine through darkness without turning the darkness itself into a warm room. Stars do heat some material in space. This is important, because the answer is not that starlight never warms anything until it reaches a planet. Gas clouds, dust grains, comet surfaces, asteroid surfaces, and the upper atmospheres of planets can all absorb radiation and warm. Around young hot stars, ultraviolet light can energize nearby gas. Dust in nebulae can absorb starlight and re-radiate it as infrared. The solar wind carries energetic particles outward from the sun. Space is not perfectly empty, and stars do interact with the material around them. But that material is usually spread very thinly compared with air on Earth. The heating is local, patchy, and dependent on what is available to absorb the radiation. It does not turn the general vacuum into a warm blanket. A campfire also needs air to exist in the first place. The flames you see are a chemical reaction between fuel and oxygen. Wood heats up, gases escape, oxygen reacts with them, and light and heat are released. Without air, a campfire cannot burn in the ordinary way. A star does not burn like wood. It does not need oxygen from outside. Its energy comes from processes in its core, where light elements are transformed under immense pressure and temperature. This is why saying a star is on fire is useful as a casual image but not quite accurate. A star is not a campfire scaled up. It is a self-contained gravitational furnace, held together by its own mass, producing energy deep inside itself. That difference matters because campfire heat begins in a small chemical flame surrounded by air, while star heat begins in an enormous plasmasphere surrounded by vacuum. The campfire gives energy directly into its environment because the environment is touching it. The star releases radiation from its surface into space, and after that the energy travels until it meets matter. A campfire and a star both glow, both warm nearby objects, and both make humans stare quietly for longer than expected, but they operate in very different physical settings. The idea that stars should warm all of space also runs into the problem of scale. Space is not just big. It is big in a way that defeats normal comparisons. The distance from Earth to the Sun is already vast, yet it is tiny compared with the distance between stars. The distance between stars is small compared with the size of a galaxy. The distance between galaxies is larger still. There is so much emptiness that even billions of stars do not fill it with warmth. Their radiation spreads, weakens with distance, and often travels for ages before being absorbed. The universe is not a crowded fireplace. It is a huge volume with bright islands scattered through it. If stars were packed much closer together, space would be a very different place. In dense star clusters, the night sky from a planet might be far brighter. More starlight would arrive from many directions. A planet there could receive extra radiation depending on its location. Near the centre of some galaxies, where stars are more crowded, the background of starlight is stronger. But even then, there is still no thick universal air carrying heat from star to star. Radiation remains the main messenger over empty distances. Brightness can increase without creating the same kind of warmth as a room full of air. This leads to a subtle point about radiation. Radiation does not need matter to travel. That is why sunlight can cross space at all. Sound cannot do this in the same way, because sound is a vibration travelling through matter. In empty space, there is no air to carry ordinary sound waves. A star can emit light across the vacuum, but it cannot send warmth by hot wind in every direction unless particles are actually travelling outward, and even then those particles become extremely spread out. Radiation is efficient at crossing emptiness. It is not efficient at warming emptiness unless there is enough matter to absorb it. So the vacuum of space is not like air waiting to be heated. It is more like a stage where light can cross without much interference. A photon leaving the sun may travel through space almost undisturbed until it lands on Earth, or on a dust grain, or on a spacecraft panel, or continues past the planets into interstellar space. It does not spend the journey warming the vacuum, because the vacuum has little to take from it. Energy transfer requires interaction. Without interaction, the radiation just keeps moving. This is one reason the sun can warm Earth so effectively. Earth is not empty. Earth is a target. It has size, surface, air, water, and chemistry. When sunlight arrives, some is reflected back to space, and some is absorbed. The absorbed portion increases the motion of particles in the ground, ocean, and atmosphere. Then heat moves through the planet system. Air rises, water evaporates, clouds form, winds blow, currents shift, storms build, forests grow, and people complain about humidity with great seriousness. All of that begins because matter catches sunlight and turns it into thermal motion and weather. Space between the sun and Earth does not do those things. It does not have oceans to warm. It does not have clouds to form. It does not have soil to bake. It does not have enough gas to stir into wind. It is crossed by sunlight but not transformed into climate. The star provides the energy. Matter decides what happens next. This distinction also helps explain why greenhouse warming on Earth is not simply about the sun being hot. Earth absorbs sunlight and then emits infrared radiation back towards space. Certain gases in the atmosphere absorb and re-emit some of that outgoing infrared radiation, slowing the loss of heat. The atmosphere changes the balance between incoming and outgoing energy. Space itself does not play that role. It is the place energy escapes to once it leaves the planet. The warmth of Earth is maintained by a balance, not by the surrounding vacuum being warm. A campfire has a balance too, but a more immediate and familiar one. Fuel burns. Heat warms the air and nearby objects. Air currents carry energy away. You move closer or farther depending on comfort. If the fire is too strong, you shift your chair back. If it fades, you add wood. Everything is happening in a thick, interactive environment. That is why the campfire analogy is emotionally useful but physically limited. It helps us understand radiation from a glowing source, but it misleads us about the role of air. The sun does not heat the vacuum around Earth into a comfortable zone. It illuminates Earth, and Earth becomes comfortable because of its own properties. Move a planet close to the sun, and it receives more radiation. Move it farther away, and it receives less. Give it an atmosphere, and the atmosphere can trap, move, and transform heat. Remove the atmosphere, and temperatures may swing wildly. Change the surface, the clouds, the rotation, the oceans, and the story changes again. The star is the source, but the environment determines the result. That is why two worlds receiving sunlight can feel completely different. Mercury is close to the sun and has very little atmosphere, so its sunlit side can become extremely hot, while its night side becomes very cold. Venus is farther from the sun than Mercury, but its thick atmosphere traps heat so strongly that its surface is hotter than Mercury's average surface conditions. Mars receives less sunlight than Earth and has a thin atmosphere, so it is generally cold, with large temperature changes. The same basic star shines on all of them. Their temperatures depend on distance, atmosphere, surface, rotation, and heat storage. Stars do not simply impose one temperature on everything around them. The campfire image also fails because a campfire has a small zone of influence, while a star has a large but thinning field of radiation. If you double your distance from a campfire, the change in warmth is obvious because you are already close and the environment is complicated. With a star, distance changes the intensity of radiation in a predictable way, but space remains empty along the route. A planet at the right distance may receive a life-supporting amount of energy. A planet too close may receive too much. A planet too far may receive too little. Between them, the vacuum is mostly a silent corridor for light. There is another everyday clue. On a clear, sunny day in the mountains, you may feel strong sunlight on your skin while the air remains cold. This can happen because sunlight is radiation heating your skin directly, while the thin mountain air does not hold or deliver heat the same way denser warm air might. Skiers know this well. You can get sunburned while standing on snow. Your face may feel warm in the sun and cold in the wind at almost the same time. That is a small earthly taste of the separation between radiation and air temperature. Space takes that separation much further. In orbit, the separation becomes sharper still. A spacecraft in sunlight absorbs radiation. In shadow, it loses heat by radiation. There is no surrounding air to carry warmth from one side to the other externally. Engineers may rotate spacecraft to even out heating, use reflective coatings, install heaters, add radiators, and carefully manage internal heat flow. They are not trying to make the surrounding space warmer. They are trying to control the spacecraft's own energy balance in a place where the environment does not help much. It is tempting to ask why all the radiation from all the stars does not eventually build up and warm the universe. Some of it does get absorbed by dust and gas, then re-emitted at longer wavelengths. Some contributes to faint backgrounds of radiation. But the universe is expanding, and radiation stretches as space expands. Light from distant galaxies can lose energy in that process. The universe also has a finite age, so not all light from every possible source has reached every place. Stars are born and die. Matter clumps into galaxies instead of filling space evenly. The result is not a universe heated uniformly by all its stars, but one with hot sources, warm objects, thin gas, cold dust, dark gaps, and a very cold background glow. That background glow is important because it sets a kind of cosmic floor for deep isolation. Far from stars, an object would still receive the faint leftover radiation from the early universe. That radiation is extremely cold by human standards. If the object had no internal heat and no nearby star, it would eventually settle close to that deep background temperature. But near a star, the balance changes. In sunlight, the object warms. In shadow, it cools. Again, the word space covers many conditions, not one simple freezer setting. So when people say space is cold, they're often describing what happens when matter is not receiving strong radiation and is free to radiate its own heat away. When people say stars are hot, they are describing dense, energetic objects producing and emitting enormous radiation. These facts fit together once we stop expecting stars to warm the vacuum like flames warm air. A fire warms a campsite because the campsite is full of interacting matter. A star warms a planet because the planet intercepts radiation. A fire heats air because air touches the flame. A star does not heat empty space much because empty space offers almost nothing to touch. A campfire creates a warm bubble in the atmosphere. A star creates a field of radiation across distance. A person beside a fire is warmed by glowing embers, hot gases, and heated surroundings. A planet beside a star is warmed by absorbed light and by how well it can store and redistribute that energy. Once this is understood, the universe feels less contradictory. It is not strange that stars are hot and space is cold. It would be stranger if the vacuum did behave like air, because then the night sky, planetary climates, spacecraft engineering, and even the visibility of distant stars would be completely different. The coldness of space is part of the same emptiness that allows light to travel across it. The stars do not fail to warm space. Space simply lacks the material required to become warm in the way a campsite does. And this brings us toward the emptiness itself, because the vacuum is not just a backdrop in this story. It is the main reason the story works. To understand why heat behaves so differently beyond Earth, we have to spend time with the strange, nearly empty regions between worlds, where there is too little matter for wind, too little matter for sound, and too little matter for warmth to spread the way our bodies expect. The emptiness between worlds is easy to underestimate because the word emptiness sounds simple. It suggests a blank space, a gap, a nothing, the quiet distance between more interesting things. A planet is interesting. A moon is interesting. A star is definitely interesting, especially if it is large enough to rearrange the future of everything orbiting it. But the space between them can sound like the pause between notes, useful only because it separates the objects we actually want to study. Yet in physics, the pause matters. The vacuum between worlds is not just a backdrop. It is the reason heat behaves so strangely away from Earth. It is the reason sunlight can cross millions of kilometers without warming the space it passes through. It is the reason spacecraft can overheat in sunlight and freeze in shadow. It is the reason the universe can be full of burning stars while still feeling, in most directions, deeply cold. On Earth, we almost never experience true emptiness. Even an empty room is not really empty. It is filled with air, dust, moisture, faint smells, tiny drifting fibers, sound waves, and a constant exchange of heat between walls, floors, furniture, and your own body. If you wave your hand through the room, you feel almost nothing, but your hand is pushing through a sea of gas. Molecules of nitrogen, oxygen, argon, carbon dioxide, and water vapor are colliding with your skin at high speed every moment. You do not notice each collision because there are too many, too small, too evenly spread. Together they become pressure. Together they become air. Together they become the invisible material your body expects to be there. That expectation is ancient. Every land animal evolved under pressure from an atmosphere. Every breath depends on it. Every sound in a conversation depends on it. Every breeze, every cloud, every flame in a fireplace, every scent of rain on pavement, every sigh that fogs a window, all of it depends on matter filling the space around us. Our senses are trained by a crowded world. We think of empty as meaning there is no chair in the corner, no person in the hallway, no water in the cup. But space is empty in a much more serious way. It is empty compared with the atmosphere, empty compared with oceans, empty compared with soil, empty compared with the inside of a living body. It is so thin that the habits of heat and sound and touch begin to break down. A vacuum means a region with very little matter. It does not have to mean perfect nothingness, and in the real universe it almost never does. Even the space between planets contains particles from the solar wind, bits of dust, stray atoms, magnetic fields, radiation, and passing light. The space between stars contains thin gas, dust grains, cosmic rays, and ancient radiation left over from the early universe. The space between galaxies is thinner still, but even there, it is not absolute nothing. The universe is not a perfectly cleaned laboratory chamber. It is more like an enormous landscape where matter is spread unevenly, gathered into stars and planets in some places, stretched into faint traces elsewhere. Still, by everyday standards, space is astonishingly empty. At sea level on Earth, a small volume of air contains an enormous number of molecules. They collide constantly, sharing energy so quickly that temperature feels like a smooth property of the air around you. In interplanetary space, the number of particles in the same volume is drastically smaller. In interstellar space, it can be smaller again. In intergalactic space, matter becomes so sparse that a particle may travel a very long distance before meeting another one. This changes everything. Heat transfer by contact becomes weak. Convection disappears except inside places where gas is dense enough to flow as a fluid. Sound cannot travel in the familiar way. There is no wind in the ordinary sense, no air pressure on your skin, no surrounding material to carry warmth from one place to another. This is why vacuum can act like an insulator. A vacuum flask keeps tea warm or water cold because it removes most of the matter between the inner and outer walls. With fewer particles in between, heat has fewer paths to travel by direct contact or moving fluid. The drink still exchanges energy by radiation, and some heat can still move through the neck and supports of the flask, but the vacuum greatly slows the process. Space works with the same principle on a grand scale. If there is almost no matter between a warm object and the darkness around it, then heat cannot simply flow away by air currents. It must leave mainly as radiation, unless the object is touching something else. This is one of the reasons the idea of space as icy air is misleading. There is no icy air. There is not enough air to behave like air at all. If you placed a warm metal ball in a cold room, the ball would lose heat to the air, and the air would carry that heat away. If you placed the same ball in deep space, far from sunlight, it would cool by radiating energy outward. The loss could be steady and severe over time, but it would not be the same as sitting in a blast of freezing wind. The coldness comes from the ability of heat to leave without much returning, not from being surrounded by a dense cold substance. The vacuum between worlds also affects how stars give energy to their surroundings. A star is not warming a thick medium in the way a heater warms a room. It sends radiation outward. That radiation crosses the vacuum efficiently, because there are few particles to block it. If space were dense, starlight would be absorbed and scattered more often. The sky would be foggier. Distant stars and galaxies would be harder to see. But because space is so thin, light can travel for immense distances. The same emptiness that prevents warmth from spreading like air also allows light to move with remarkable freedom. This is a quiet trade at the heart of astronomy. Space is cold because it is empty, and space is visible because it is empty. We see the stars because their light can cross the vacuum. We do not feel most of their heat because that light is spread thin by distance and only warms matter when it is absorbed. The vacuum is not doing nothing. It is deciding by its lack of matter which forms of energy transfer are possible and which are weak. Between Earth and the Sun, the vacuum is not perfect, but it is thin enough that sunlight travels almost unimpeded. The solar wind streams outward, carrying charged particles from the Sun. Dust drifts through the inner solar system. Magnetic fields twist and interact. Yet compared with the atmosphere of Earth, this region is extremely empty. A photon leaving the Sun can cross the distance to Earth without needing air, without heating a path, without pushing through a warm medium. When it reaches Earth, the story changes. It strikes molecules, clouds, oceans, leaves, roofs, and rocks. Some of it is reflected, some is absorbed. Absorbed light becomes thermal motion. Thermal motion becomes warmth. Warmth becomes weather. The vacuum allowed the energy to arrive, but matter turned it into a lived environment. This helps explain why planets are thermal machines. A planet is not just a rock waiting in space. It is an object that absorbs energy, emits energy, stores heat, moves heat, and sometimes traps heat. Earth has an atmosphere and oceans, so it redistributes energy constantly. The Moon has almost no atmosphere, so its surface responds much more directly to sunlight and darkness. Mars has a thin atmosphere, so it has some weather but limited heat storage compared with Earth. Venus has a dense atmosphere, so heat becomes trapped and circulated in a very different way. The vacuum around these worlds is similar in the sense that it is thin, but the worlds themselves are very different because matter is arranged differently on and around them. A vacuum also makes shadows more powerful. On Earth, shade is rarely absolute cold because warm air still surrounds you. Stand beneath a tree on a sunny day and the direct sunlight is blocked, but the air under the tree has been warmed by the ground, nearby surfaces and moving currents. The shade is cooler, not a separate universe. In space, shadow can be much more severe because there is no thick atmosphere to bring heat from the lit side. A crater near the pole of the Moon, if it never receives sunlight, can remain extremely cold for very long periods. Some of these shadowed regions can preserve ice because they are shielded from direct solar heating and have little environmental warmth to disturb them. Darkness in a vacuum can become a deep thermal isolation. The same principle affects spacecraft. A satellite orbiting Earth may pass repeatedly from sunlight into the shadow of the planet. In sunlight, surfaces absorb radiation and warm. In shadow, they radiate energy away towards space. The satellite moves through these conditions again and again. Engineers must make sure it does not expand and contract too much, does not overheat, does not let batteries become too cold, and does not allow instruments to drift outside their operating ranges. The vacuum gives no simple comfort. It removes air resistance, which is useful for orbit, but it also removes the easy cooling and warming that air provides on the ground. Inside a spacecraft, air and materials restore some of the familiar physics. There is pressure, there is gas, there are fans to move air, there are surfaces that conduct heat, there are people and machines producing warmth. But the spacecraft as a whole still sits in vacuum. It must eventually get rid of excess heat by radiation. This is why spacecraft often have radiator panels. They provide surfaces designed to release infrared radiation into space. On Earth, a machine can be cooled by blowing air over it. In space, a machine must pass its heat to a radiator and let that radiator shine the energy away. Heat becomes something that must be managed with surfaces, coatings, orientation, and careful design. The vacuum between worlds also changes the meaning of boiling and evaporation. On Earth, water stays liquid at ordinary temperatures because atmospheric pressure helps hold it in that state. In a vacuum, exposed liquid water behaves very differently. With little external pressure, it can boil at lower temperatures and at the same time evaporation can remove heat rapidly, causing freezing. This is one reason unprotected living tissue would face severe danger in space. The issue is not just cold, it is pressure. Our bodies are adapted to an environment pushing inward from all sides. Remove that pressure, and gases expand, liquids behave differently, and breathing becomes impossible. The vacuum is not merely a temperature problem, it is a whole change in physical conditions. That matters because popular images often reduce space to coldness alone. A character is thrown into space, and the scene becomes instant frost. Reality is more complicated. The lack of oxygen would lead to unconsciousness quickly. The lack of pressure would be extremely dangerous. Heat loss would happen, but not like plunging into cold water. Direct sunlight could heat exposed surfaces. Shadow could cool them. Moisture could evaporate. The body is not designed for any of it. Space is hostile not because it is one simple thing, but because it removes nearly everything life depends on at once. Yet the vacuum is also what makes orbital motion so graceful. With little matter to create drag, objects can keep falling around planets for long periods. A satellite in a low orbit still feels a faint trace of atmosphere, and slowly loses altitude over time. But higher up, the vacuum is thin enough that motion can persist with little resistance. Planets travel around the Sun through space without ploughing through a thick cosmic gas that would slow them quickly. Moons orbit planets. Comets sweep inward and outward. Dust spirals slowly under subtle forces. The emptiness allows the clockwork of gravity to continue with astonishing patience. There is a useful contrast with the ocean. Move through water, and water pushes back strongly. Move through air, and air pushes back less strongly, but still enough that planes, birds, and falling leaves must account for it. Move through the vacuum of space, and there is far less resistance. This does not mean motion is effortless in every way. Changing speed or direction still requires force. But once moving, an object does not need constant pushing to keep going. This is another place where Earth intuition misleads us. We are used to friction. Space is closer to the clean version of motion described in physics, where an object continues unless something acts on it. The same lack of matter that reduces drag also reduces sound. Sound is a pressure wave moving through a medium. In air, molecules bump into one another, passing the disturbance along. In water, sound travels differently but still needs the water. In a solid, vibrations can travel through the structure. In a vacuum, there is no ordinary medium to carry the wave. A spaceship explosion would release energy and debris, and it might produce vibrations inside nearby objects if material struck them. But there would be no booming sound travelling through empty space to your ears. Science fiction often gives space sound because silence is difficult for drama, and because audiences like engines to roar. Physics is less theatrical. In vacuum, the stars shine quietly. That quietness is part of the same story as coldness. Both come from the scarcity of particles. No particles means no ordinary sound. Few particles means little heat transfer by collision. No thick gas means no weather between planets. Radiation and gravity remain, and they are enough to shape the universe, but they do not create the familiar sensory world our bodies expect. Space is not empty of activity, but it is empty of the kind of matter that makes environments feel touchable. At the same time, it would be wrong to imagine the vacuum as perfectly clean and still. The space between planets is crossed by streams of charged particles. The sun releases the solar wind, which flows outward and interacts with planetary magnetic fields. Around Earth, this interaction helps create auroras, those curtains of light near the poles. The particles themselves are sparse compared with air, but they can have important effects because they are energetic and electrically charged. Space weather can disturb satellites, communication systems, and power grids on Earth. So the vacuum is not dead. It is thin but active. Dust also matters. Tiny grains move through space, remnants of comets, asteroids, collisions, and the formation of planets. When these grains enter the atmosphere of Earth, they can burn as meteors, making brief streaks of light. In deep space, dust can absorb starlight and emit infrared radiation. Large clouds of dust can hide stars behind them or glow when warmed by nearby stars. Again, the vacuum is not absolute emptiness. It has ingredients, just spread so thinly that ordinary heat flow does not behave as it does in air. The space between stars, called interstellar space, contains gas and dust at densities far lower than anything we would call air. Some regions are warmer, some colder, some ionized, some molecular, some shaped by old supernova explosions, some compressed into clouds that may one day form new stars. These clouds show that emptiness is not the same everywhere. A dense molecular cloud is still an excellent vacuum by Earth standards, but compared with the regions around it, it can be rich with material. Gravity can gather that material slowly. Over time, parts of a cloud can collapse, heat up, and ignite into new stars. So even the vacuum between stars is not only a gap, it is part of the life cycle of stars. Between galaxies, matter is thinner still, but not absent. Hot gas can fill galaxy clusters. Faint particles drift through immense volumes. Radiation passes through. Dark matter, which does not interact with light in the ordinary way, shapes the large-scale structure of the cosmos through gravity. The universe is a web of matter and emptiness, with galaxies along vast filaments and great voids between them. The word vacuum covers many levels of thinness, from the space above the atmosphere to the enormous cosmic voids where galaxies are scarce. All of it is empty compared with Earth, but none of it is simple nothing. The vacuum also affects time in a practical sense for heat. If a warm object is placed in a dense cold environment, it may cool quickly. If it is placed in vacuum, it may cool more slowly at first because conduction and convection are removed. But if it is exposed to deep space and has good radiating surfaces, it can eventually become very cold. The final temperature depends on balance. Is sunlight arriving? Is infrared radiation arriving from a planet? Is the object producing internal heat? How well does it emit radiation? How well does it reflect light? In space, temperature is a negotiation between radiation sources, material properties, and geometry. Geometry matters more than we might expect. Which way is a surface facing? Is it pointed toward the sun, toward a planet, toward deep space, or toward another part of the spacecraft? A flat panel in sunlight may heat differently from one angled away. A shiny surface may reflect much of the incoming light, while a dark surface may absorb more. A white coating may keep equipment cooler. A radiator may need a clear view of dark space to release heat efficiently. In vacuum, the direction of exposure becomes crucial because there is no air to blur the difference. This directional nature is one of the strangest differences from life on the ground. In a room, the air mixes, heat spreads. A wall in sunlight may warm the room. A heater in one corner can eventually affect the other side. In space, a surface can face a furnace in one direction and a cosmic refrigerator in another. The object itself must conduct heat internally if it is going to even out the difference. If it cannot, one part may become hot while another remains cold. The vacuum does not help with sharing. It is also worth noticing that vacuum does not pull heat out of something by suction. That image is common because we speak of vacuum as if it sucks. A vacuum cleaner works because air pressure pushes air and dust into a lower pressure region created by the machine. Space itself is not actively sucking heat away. Heat leaves by radiation, because warm objects emit energy. Gas expands into vacuum because particles move outward when no pressure holds them in. The vacuum is not grabbing, it is allowing. It allows gases to expand, allows radiation to escape, allows objects to move with little resistance, allows light to cross huge distances. Its power is often the power of not getting in the way. That lack of interference is why telescopes in space can see so clearly. Above the atmosphere, there is no air turbulence to blur images, no weather, no clouds, and less absorption of certain kinds of light. Space telescopes take advantage of the vacuum and the absence of atmospheric interference, but they also have to survive it. Their mirrors and instruments must be kept at controlled temperatures. Some infrared telescopes need to be extremely cold, so their own heat does not overwhelm the faint heat signals they are trying to detect from distant objects. To observe the cold universe, a telescope must often become cold itself, shielded from the sun and earth, radiating its heat into space. This brings the vacuum back to the central question. Space can be cold because it is not filled with matter that stores and shares the energy from stars. It can also help instruments become cold because it lets them radiate heat away into darkness. At the same time, it can expose them to intense sunlight that would warm them dangerously. The vacuum is not simply cold or hot. It is an environment where the usual carriers of heat are missing. That absence makes thermal conditions depend strongly on radiation and design. For living beings, this makes space profoundly unnatural. We're not only warm bodies, we are wet bodies, breathing bodies, pressure-dependent bodies, bodies built to exchange heat with air and surfaces in a narrow range of conditions. Our comfort depends on a surrounding medium. Space offers no such medium. A spacecraft or suit must create it artificially, holding pressure, providing oxygen, removing carbon dioxide, controlling humidity, and managing heat. In a very real sense, every human presence in space is surrounded by a small manufactured Earth. Not a planet, of course, but a pocket of pressure and warmth and breathable gas carried into the vacuum. The vacuum between worlds is therefore not a passive emptiness. It is an active condition that shapes every journey. It decides how heat moves, how sound fails, how bodies survive, how spacecraft are built, how planets cool, how sunlight travels, and how distant stars remain visible. It is the open sea of the solar system, except thinner than any sea, quieter than any desert, and less forgiving than any winter. It does not freeze things by touching them. It changes the rules by barely touching them at all. And once that is clear, the next question becomes more specific. If space has almost no matter, and heat cannot travel through it the way it travels through air or water, then how does heat travel there at all? Sunlight reaches Earth, spacecraft radiate warmth away. Dust grains absorb starlight. Planets glow faintly in infrared. The vacuum removes some paths for heat, but not every path. What remains is the most important messenger of warmth across the universe, light itself, carrying energy through emptiness without needing a single breath of air. So heat has to become a traveller of a different kind. On Earth, warmth has many helpers. It can pass through the handle of a pan, move with steam above a kettle, ride a breeze across a room, or flow through water in a bath. It can spread through walls, floors, blankets, pipes, hands, and the air itself. Our world is crowded with matter, and matter gives heat plenty of ways to move. But in space, most of those helpers vanish. There is almost no air, almost no water, almost no surface connecting one place to another. A warm object cannot rely on a surrounding atmosphere to carry energy away. A cold object cannot rely on nearby air to bring warmth in. The usual routes are blocked, and yet heat still travels. It travels by light. That may sound strange at first because we tend to think of light as something we see, not something we feel. But light is more than brightness. Light is a way for energy to move. Some light is visible to our eyes like sunlight, firelight, and the glow of a lamp. Some light is invisible to us like infrared, ultraviolet, radio waves, and X-rays. These are not separate magic substances. They are different forms of electromagnetic radiation, and all of them can carry energy through empty space. This is how the sun warms Earth. The energy does not need air between the sun and our planet. It leaves the sun as radiation, crosses the vacuum, reaches Earth, and is absorbed by matter here. Once absorbed, it becomes part of the motion of atoms and molecules. That is when light becomes warmth. A simple way to picture this is to think about standing near a window on a cold but sunny day. The air in the room may be cool, yet sunlight falling on your hand feels warm. The glass does not need to become hot first. The sunlight passes through, reaches your skin, and your skin absorbs some of that energy. If you move your hand into shade, the warmth fades. The same thing happens on a much larger scale in space. Radiation can cross an empty region, and then warm whatever absorbs it. The empty region itself does not have to warm up along the way. This is the reason Earth can receive heat from the Sun despite the vacuum between them. If heat could only travel by contact, our planet would be in serious trouble. There is no solid bridge from the Sun to Earth. There is no warm river of air flowing through space. There is no cosmic wind in the everyday sense carrying sunlight like a breeze carries the smell of smoke. Instead, the Sun releases radiation in every direction. A tiny portion of that radiation intersects Earth. Some is reflected by clouds, ice, deserts, and bright surfaces. Some is absorbed by land, ocean, atmosphere, and living things. The absorbed part becomes thermal energy, and that energy then moves around Earth through air, water, and ground. This gives us a useful order of events. Across the vacuum, heat travels mainly as radiation. Once it reaches a planet, heat can move by the more familiar methods again. Sunlight warms the ground warms the air touching it. Warm air rises, cooler air moves in, oceans absorb energy and carry it in currents. Clouds form, winds blow, weather begins. Space delivers the energy by radiation, but Earth turns that energy into climate through matter. Without matter, radiation keeps going. A ray of sunlight leaving the Sun does not gradually spend itself warming empty space. If it does not hit much, it travels onward. It may pass the orbit of Mercury, cross the orbit of Venus, reach Earth, continue past Mars, and move out toward the outer solar system if nothing absorbs it first. Some sunlight eventually leaves the solar system altogether and joins the faint glow of starlight moving through the galaxy. This is one of the most important differences between radiation and heat flow through matter. Warm air spreads and mixes. Radiation travels until it interacts. When radiation hits matter, several things can happen. It can be reflected, which means it bounces away. It can pass through, if the material is transparent to that kind of radiation, or it can be absorbed, which means its energy is taken up by the material. Absorption is what matters most for warming. A black shirt in sunlight warms faster than a white shirt, because it absorbs more visible light and reflects less. A shiny metal surface may stay cooler because it reflects a lot of incoming radiation. A dark rock on the moon can heat strongly in sunlight because it absorbs energy and has little air around it to carry that energy away. This is why colour, texture, and material matter so much in space. A spacecraft surface is not chosen only to look tidy in photographs. Its reflectivity and ability to emit infrared radiation are part of its survival. A surface that absorbs too much sunlight may overheat. A surface that radiates too efficiently in shadow may become too cold. Engineers choose coatings, blankets, panels, and orientations to control how energy enters and leaves. In a vacuum, the outer skin of a spacecraft is not just a shell. It is part of a thermal conversation with the Sun, Earth, and deep space. Every warm object also emits radiation of its own. This is not only true of stars and flames. Your body does it right now. A mug of tea does it. A sleeping cat does it with great confidence. A planet does it. The radiation from ordinary warm objects is mostly infrared, invisible to human eyes but detectable by thermal cameras. That is why a thermal image can show warm bodies in darkness. The objects are glowing, just not in the kind of light our eyes can see. In space, this infrared glow is one of the main ways objects lose heat. With no air to carry warmth away, they must radiate it. This is why a warm spacecraft can cool by facing a radiator toward deep space. The radiator is a surface designed to emit infrared radiation efficiently. Heat from inside the spacecraft is moved to the radiator, and the radiator sends energy away as invisible light. The energy crosses the vacuum and does not need air to carry it. If the radiator has a clear view of cold dark space and is shielded from sunlight, it can lose heat effectively. This sounds simple, but the design is delicate. A radiator that sees too much sunlight will absorb energy instead of just losing it. A radiator facing a warm planet may receive infrared radiation back. The spacecraft must manage where its surfaces point and what they are exposed to. The same idea applies to planets. Earth absorbs sunlight and also emits infrared radiation back toward space. The temperature of Earth depends on the balance between energy coming in and energy going out. If more energy arrives than leaves, the planet warms. If more leaves than arrives, it cools. The atmosphere affects this balance by absorbing and re-emitting some infrared radiation, which slows the escape of heat from the surface. The Moon also absorbs sunlight and emits infrared radiation, but because it lacks a thick atmosphere and oceans, its surface temperature changes much more dramatically. During the long lunar day, sunlight heats the ground. During the long lunar night, the ground radiates energy into space and cools deeply. This balance is not only for planets and spacecraft. It applies to dust grains, asteroids, comets, moons, telescope mirrors, and even the tiny particles drifting between stars. A dust grain near a bright star absorbs radiation and warms. Then it emits infrared radiation and cools. Its temperature settles where absorption and emission balance. Move the same grain farther from the star and it receives less radiation, so it settles at a colder temperature. Place it in a dense cloud where starlight is blocked, and it can become extremely cold. Radiation is the constant exchange, the quiet accounting of energy in the vacuum. There's a useful everyday example in a clear night sky. After sunset, the ground often cools by radiating infrared energy upward. If the sky's cloudy, the night tends to stay warmer because clouds absorb and emit infrared radiation back downward. If the sky's clear, more infrared energy escapes to space, and the ground can cool more quickly. This is why frost can form on clear nights even when the day was mild. The ground is radiating heat away into the open sky. Earth's atmosphere still plays a role, of course, but the basic principle is the same. A clear view of space is a path for heat to leave. This is also why deserts can have hot days and cold nights. Dry air and clear skies allow heat to escape efficiently after sunset. During the day, sunlight heats the ground intensely. At night, with a little moisture and few clouds to trap outgoing infrared radiation, the surface loses energy quickly. The desert is still filled with air, so it is not the same as space, but it gives a small familiar taste of radiative cooling. When the sun is present, radiation brings energy in. When the sun is gone, radiation carries energy out. In deep space, far from stars, there is still radiation. The universe is not perfectly dark in a physical sense. There is faint starlight, infrared emission from dust, energetic particles, and most importantly, the cosmic microwave background, the cooled leftover glow from the early universe. This background radiation reaches from every direction. It is very weak and very cold by human standards, but it is not nothing. An object placed far from stars with no internal heat would eventually exchange radiation with this background. It would lose its own heat until it approached the temperature set by that faint glow. That is one of the reasons deep space has a baseline coldness. Not because cold air surrounds everything, but because the radiation coming back from the universe is so faint. Radiation can also heat without making contact, which is why sunlight can be dangerous in space. On Earth, the atmosphere blocks some harmful radiation and scatters light across the sky. It also helps spread heat. In space, an unprotected surface can receive direct solar radiation, with no clouds, no air, and no shade unless something physically blocks the line of sight. A spacecraft near Earth may receive strong sunlight, reflected sunlight from Earth, and infrared radiation from Earth itself. Then, during eclipse, it may suddenly lose direct sunlight and begin cooling. The environment changes as the spacecraft moves. Heat arrives and leaves through radiation, and the timing matters. This is why rotation can be useful. Some spacecraft rotate slowly to distribute sunlight over their surfaces, reducing extremes. If one side constantly faces the sun, it may become much hotter than the side facing darkness. Rotation lets different surfaces take turns absorbing and radiating energy. Other spacecraft maintain fixed orientations because their instruments or solar panels need to point in certain directions. Then engineers must solve the thermal problem with insulation, heaters, radiators, louvers, and careful material choices. Spacecraft do not simply float in cold. They are constantly balancing radiation from multiple sources. Insulation in space also works differently than a thick winter coat. A coat keeps you warm mostly by trapping air near your body and slowing convection. In a vacuum, trapped air is not the main issue outside the spacecraft. Multi-layer insulation used on spacecraft works by reducing radiative heat transfer. It often consists of many thin reflective layers separated so that radiation is reflected again and again, rather than passing easily through. This is why spacecraft often appear wrapped in shiny gold or silver material. It is not decoration. It is a carefully designed barrier against energy exchange by radiation. The gold colour often seen on spacecraft is not always actual gold in the ordinary jewellery sense, though some materials may have metallic coatings. The important point is that shiny reflective layers can reduce absorbed sunlight and slow radiative heat transfer. They help keep instruments from heating too much or cooling too quickly. In space, the difference between comfort and failure can depend on how a surface treats light that cannot be seen by human eyes. Heat can still move through spacecraft by conduction. If one part of a metal structure is warm, energy can travel through the material to cooler parts. This is useful when engineers want to guide heat from electronics to radiators. It can be a problem when heat leaks into places that need to stay cold. Since there is little external convection, internal conduction becomes one of the main tools for moving heat where it needs to go. Heat pipes are often used for this purpose. They can transfer thermal energy efficiently within spacecraft, helping spread heat from hot components to radiating surfaces. The heat still leaves the spacecraft by radiation, but first it must be carried to the right place. Inside a crewed spacecraft, convection can happen because the cabin contains air. Fans are important because warm air does not rise in microgravity in the usual way. On Earth, warm air rises because gravity and density differences produce buoyant motion. In orbit, without the same effective up and down inside the cabin, warm air and carbon dioxide can linger unless fans move them. This is a reminder that even inside a spacecraft, heat and air behave differently. Engineers must create circulation deliberately. The cabin is a small artificial environment, and it needs active management. Outside, in vacuum, there is no such circulation. If a tool is left in sunlight, it can heat. If left in shadow, it can cool. If it is attached to a structure, conduction may share energy with that structure. If it is isolated, radiation dominates. A small object may change temperature faster than a large one because it has more surface area compared with its stored heat. A large object may warm and cool more slowly. Shape matters. Surface matters. Direction matters. Heat in space is a geometry problem as much as a temperature problem. The sun is the strongest radiation source for objects in the inner solar system, but it is not the only one. Earth emits infrared radiation because it is warm. It also reflects sunlight. For satellites in low Earth orbit, Earth fills a large portion of the sky, so it becomes an important thermal influence. A spacecraft around Jupiter must consider radiation from the Sun, from Jupiter, from its own systems, and from charged particles trapped in Jupiter's powerful magnetic environment. A probe travelling far from the Sun receives much less solar radiation, so it may need internal heaters or radioactive power sources to keep instruments warm. As distance changes, the thermal story changes. This is why outer solar system missions are difficult. Far from the sun, solar panels receive weak light, and the environment becomes colder in terms of incoming radiation. Spacecraft need power and heat. Some missions use radioisotope power systems, which produce electricity and useful warmth from the decay of radioactive material. That heat is not coming from the cold space around them. It is carried from within, a small internal source that keeps the spacecraft alive in the dark. Again, survival depends on balance. Too near the sun, the problem is rejecting excess heat. Far from the sun, the problem is keeping enough heat and power. Comets show another side of radiative heating. Far from the sun, a comet is a cold body of ice, dust, and rock. As it moves closer, sunlight warms its surface. Ice can turn into gas, carrying dust outward and forming a coma and tail. The tail does not trail behind simply like smoke from a moving train. It is shaped by sunlight and the solar wind. A comet becomes active because radiation reaches matter that can respond. The vacuum itself does not warm, but the comet's surface does, and that changes the object dramatically. Asteroids respond more quietly. Sunlight warms their surfaces, and they radiate heat back into space. Over long periods, the way an asteroid absorbs and emits radiation can slightly affect its motion. Small effects can build over time. Even gentle thermal radiation can matter in orbital dynamics when time is long and objects are small. Heat travelling through near emptiness is not only about comfort or cold, it can shape the paths of small worlds. Dust in interstellar clouds also lives by radiative exchange. A dust grain may absorb visible or ultraviolet light from nearby stars, then emit infrared radiation. Astronomers study that infrared glow to learn about coal dust hidden in dark regions. Some places where stars are forming are blocked from visible view by dust, but infrared radiation can reveal what is happening inside. Heat travelling as radiation is not just a physical process, it is also a messenger. It tells telescopes where matter is, how warm it is, and what kind of environment it lives in. The fact that every warm object radiates also means that astronomy is partly the study of heat made visible in different wavelengths. Hot stars glow strongly in visible and ultraviolet light. Cooler dust glows in infrared. Very hot gas around energetic events may emit X-rays. Cold gas can reveal itself through radio emission. The universe speaks in radiation because radiation crosses the spaces between things. If heat needed air to travel, astronomy as we know it would be impossible. The vacuum would silence the sky. Instead, the vacuum lets radiation carry information across unimaginable distances. There is a gentle irony here. Space is cold because it is empty, but we know so much about space because that emptiness lets energy reach us. The same vacuum that prevents campfire-style warming allows ancient light to arrive at telescopes. Radiation from stars, galaxies, dust clouds, and the early universe can travel through the darkness and meet our instruments. It can warm a detector by a tiny amount, trigger an electronic signal, or leave a mark on a sensor. From those small interactions, we reconstruct the histories of stars and galaxies. Heat and light are not only physical energy, they are evidence. Still, radiation is not always gentle. High-energy radiation can damage living tissue and electronics. Earth's atmosphere and magnetic field protect life from much of it. Spacecraft beyond that protection must be hardened, shielded, and carefully operated. Solar storms can send bursts of energetic particles outward. Astronauts must be protected from radiation exposure. Instruments can be disrupted. Space heat is not only about warmth. Radiation can carry energy in forms that break chemical bonds, alter materials, and interfere with electronics. The vacuum offers no thick atmosphere to soften these effects, so heat travels through near nothingness mainly by radiation. But that simple statement contains many consequences. It explains how sunlight warms Earth. It explains why shadows in space can become so cold. It explains why spacecraft need radiators and reflective insulation. It explains why a distant star can be visible without warming us. It explains why planets glow in infrared and why telescopes can study cold dust clouds. It explains why space is not a uniform freezer, but a place of sharp contrasts where energy moves in straight lines, surfaces matter greatly, and balance determines temperature. In daily life, heat feels local and touchable. A warm mug, a heated room, a blanket, a bath. In space, heat becomes less like a substance spreading through a room and more like a message sent by light. It leaves a source, crosses emptiness, and waits for matter to answer. If the matter absorbs it, there is warming. If the matter reflects it, the energy moves on. If there is no matter, the radiation continues in silence. That is why stars can pour energy into the universe without making the vacuum itself comfortable. The energy is travelling, not settling. It warms what catches it. It passes through what does not. A planet with air and oceans can turn it into weather. A spacecraft can turn it into an engineering problem. A dust grain can turn it into a faint infrared glow. Deep space, with almost nothing available to absorb or return the energy, remains cold not because energy cannot enter it, but because there is so little there to keep it. This leads naturally to the oldest warmth still present in the universe, a faint radiation that does not come from any star we see tonight, but from the early history of the cosmos itself. It is everywhere, arriving from every direction. A leftover glow so stretched and cooled by time that it now forms the quiet background against which all other heat is measured. That faint background is one of the most important clues in all of modern cosmology, and it is also one of the quietest. It does not look like a star. It does not come from a single place. It does not blaze in one corner of the sky or announce itself like a comet with a tail. It arrives from every direction at once, so evenly and so gently that for most of human history no one knew it was there. It is called the cosmic microwave background, and although the name sounds technical, the idea behind it is deeply connected to the question that brought us here. Space is cold today, partly because the universe itself has cooled. The darkness between stars is not only empty, it is old. To understand this ancient chill, we have to imagine the universe when it was nothing like the universe we see now. Today, when we look around, we find planets, stars, galaxies, dust clouds, black holes, and great regions of thin space between them. Matter is clumped together in islands and webs. Light can travel across enormous distances. Telescopes can see galaxies so far away that their light began travelling before Earth had complex life. But the early universe was not like this. It was much hotter, much denser, and much more uniform. There were no planets, no stars, no galaxies, no quiet night sky, and no empty darkness in the familiar sense. Everything was packed into a glowing, seething state where matter and radiation were mixed together. In those early times, the universe was so hot that atoms could not hold together. The particles that would later become atoms were separated into a dense plasma. Light could not travel freely through this plasma because it kept running into charged particles. A photon would move a short distance, scatter, change direction, and scatter again. Instead of crossing the universe in a clean line, light was trapped in a crowded fog. Not a fog made of water droplets, but a hot electrical fog of particles and radiation. The universe was bright, but it was not transparent. This may sound strange because we often associate brightness with visibility. A bright room is easy to see across. A bright sky reveals the world. But brightness and transparency are not the same. The early universe was filled with light, yet that light could not travel far without being scattered. It was more like trying to see through the inside of a glowing cloud. There was energy everywhere, but there was no clear view. The universe had not yet become the kind of place where light from one region could cross space and arrive somewhere else as a message. As the universe expanded, it cooled. Expansion matters because it spreads energy out. Imagine a hot, dense gas in a container that grows larger and larger. The gas becomes thinner, and its temperature falls. The universe is not exactly a gas in a container, but the broad idea helps. As space expanded, the contents of the universe became less dense and less hot. Eventually, the temperature dropped enough for electrons and atomic nuclei to join together and form neutral atoms. This did not happen because the universe suddenly became cold by human standards. It was still very hot, but it became cool enough for atoms to exist. That moment changed everything for light. Once neutral atoms formed, the universe became much more transparent. The charged particles that had kept scattering light were no longer roaming freely in the same way. Photons could finally travel long distances without constantly being interrupted. The light that had been trapped in the early plasma was released into the newly transparent universe. It began travelling through space, and it has been travelling ever since. The cosmic microwave background is that released light, stretched and cooled by the expansion of the universe over billions of years. When it first began its long journey, it was much hotter light, associated with a universe that was still glowing. But as space expanded, the wavelengths of that light stretched. Stretched light loses energy. Visible and infrared light from the early universe became longer wavelength microwave radiation. What was once a hot glow became a cold whisper. This is one of the most important details. The background radiation is not cold because it was born cold. It is cold because the universe expanded for a very long time. The light was stretched as space itself grew. Its energy decreased. Its temperature fell. Today, that ancient radiation corresponds to a temperature only a little above the lowest possible temperature. By human standards, it is almost unimaginably cold. Yet it is everywhere. It fills the universe as a faint afterglow, arriving from every direction like the cooled memory of a time when space itself was hot and bright. This gives deep space a kind of thermal floor. If you took an object far away from stars, planets, dust clouds, and any source of internal heat and left it long enough, it would not cool to absolute nothing. It would still receive this faint background radiation. It would also radiate energy away. Over time, it would settle into balance with the radiation around it. That balance would be extremely cold, but not perfectly zero. The universe still glows, just barely. This is a very different kind of cold from the cold of a winter night on Earth. A winter night is cold because air and ground are at low temperatures compared with your body, and heat leaves you through contact, wind, and radiation. The cold associated with the cosmic microwave background is not a cold wind and not a cold surface. It is the faint radiation environment of the universe itself. It tells us how little warmth comes back from deep space when an object radiates its heat outward. The darkness is not completely empty of radiation, but what returns is very weak. That weakness matters for spacecraft and planets, though in most places near stars it is not the dominant source of heating or cooling. Near Earth, sunlight is far stronger. Earth itself emits infrared radiation. The Moon reflects sunlight. A spacecraft has internal systems generating heat. In the inner solar system, the cosmic microwave background is overwhelmed by local sources. But if we are asking what deep space is like in the absence of nearby stars, the ancient background becomes central. It is the universe's baseline glow after almost 14 billion years of expansion and cooling. The discovery of this background is one of those scientific stories that feels almost too neat, though the real process involved noise, confusion, and a stubborn antenna. In the 1960s, two researchers, Arno Penzias and Robert Wilson, were working with a sensitive radio antenna. They kept detecting a persistent noise that came from every direction. It did not seem to come from the city, the equipment, the atmosphere, or the galaxy. They checked the instrument. They removed possible sources of interference. There is even a famous detail involving pigeons nesting in the antenna, because apparently even the birth cry of the universe had to compete with ordinary maintenance problems. After the unwanted possibilities were ruled out, The signal turned out to be exactly the kind of leftover radiation predicted by Big Bang cosmology. That discovery gave scientists powerful evidence that the universe had once been hot and dense. The cosmic microwave background was not just another astronomical signal, it was a fossil. Not a fossil made of bone or stone, but a fossil made of light. It came from a time before stars existed. It showed that the universe had cooled from an earlier state. It also gave researchers a way to study the young universe directly, not by guessing from later structures alone, but by measuring the ancient radiation that still surrounds us. When scientists mapped this background more precisely, they found that it is nearly uniform, but not perfectly uniform. There are tiny variations in temperature across the sky. These variations are extremely small, but they are important. They are the early fingerprints of structure. Slightly denser regions in the young universe would later help matter gather under gravity. Over long spans of time, those small differences grew into galaxies and clusters of galaxies. In that sense, the cosmic microwave background is not only a sign of ancient heat, it is also the earliest baby picture of the cosmic structure we now inhabit. The background tells a story with two sides. On one side, it shows that the universe was once much hotter. On the other, it shows that the universe has become cold through expansion. Both sides help answer why space is cold now. The universe did not remain a hot plasma. It stretched, it thinned. Matter gathered into stars and galaxies while radiation spread out and cooled. Heat became concentrated in stars, planets, gas clouds, and energetic events, while the vast spaces between them became colder and emptier. The warmth of the early universe did not disappear in a simple way. It was diluted, transformed, and stretched into microwave radiation. This is why the phrase ancient chill is so fitting in a practical scientific sense. The cold of deep space is not merely the absence of stars nearby. It is also the result of cosmic history. The universe has aged. It has expanded. Its original radiation has cooled. A young universe was a hot universe. An older expanded universe is colder on average, with heat concentrated in places where gravity has gathered matter and powered stars. The darkness between those places carries the faint afterglow of the beginning, but that afterglow is now very cold. It is worth staying with this for a moment because it changes how we think about space. Empty space is not simply a stage that has always been dark and cold. In the early universe, space was filled with hot radiation and dense matter. Darkness, in the familiar astronomical sense, came later. Transparency came later. Stars came later. The first clear light to travel freely is now the cosmic microwave background. Before that, the universe was opaque. After that, light could move, matter could gather, and eventually the first stars could ignite. Those first stars were important because they began changing the universe chemically and visually. They produced heavier elements in their cores and in their deaths. Later generations of stars and planets formed from enriched material. The atoms in Earth, in oceans, in rocks, and in living bodies are part of that long history. But the cosmic microwave background is older than all of that. It comes from before the first stars. It is the background against which the later drama of stars unfolds. This also helps explain why stars do not simply erase the cold. Stars are local heaters in a vast and expanding universe. They can warm planets, illuminate dust, ionize gas, and shape their surroundings. But they do not return the entire universe to its early hot state. Their energy spreads outward, becomes diluted with distance, and may eventually be absorbed and re-emitted. Meanwhile, cosmic expansion continues to stretch radiation on the larger scales. The universe can contain brilliant stars and still have a cold background because the stars are concentrated sources in an immense volume. A room with a heater eventually becomes warm because the room is small, enclosed, and filled with air. The universe is not small. It is not enclosed in a wall that reflects heat back in any everyday sense. It is expanding, and much of it is extraordinarily empty. Stars shine, but their radiation does not fill a closed chamber until everything reaches one comfortable temperature. The cosmic background shows us that the universe has a thermal history, not a thermostat. This point matters when people imagine space as a perfect void of nothing at all. The cosmic microwave background reminds us that even deep space has an environment. It is just an extremely cold and faint one. If you could build an ideal detector, shield it from the sun, from Earth, from your own spacecraft, and from local sources, it would still detect radiation from every direction. That radiation would not warm the detector much, but it would be there. Space is not nothing, it has a memory. The background also tells us why there is no such thing as a perfectly dark view of the universe. Human eyes cannot see microwaves, so the background does not appear as visible light. To us, deep space looks black when there are no stars or galaxies bright enough to see. But instruments tuned to microwaves find the ancient glow everywhere. The darkness is visual, not complete. The universe is quietly shining in a form of light our eyes did not evolve to detect. Our eyes evolved under the sun, inside Earth's atmosphere, tuned to the wavelengths useful for life on this planet. We are good at seeing reflected sunlight from objects around us. We are not naturally equipped to see the cold microwave glow that fills the cosmos. Technology extends our senses. Radio telescopes and microwave instruments let us notice what the body cannot. They reveal that the night sky has layers. Visible stars are only one layer. Infrared dust is another. Radio emission, X-rays, ultraviolet light, and microwave background radiation all tell different parts of the story. The cosmic microwave background is especially powerful because it is so uniform. A signal coming from one direction could be a local object. A signal coming from the plane of the galaxy could be galactic. But a nearly uniform signal from every direction suggests something universal. It surrounds us because it belongs to the whole observable universe. We're inside it, not looking at it from the outside. Every direction in the sky looks back toward the time when the universe first became transparent. There is a subtle fact here that can sound confusing. When we observe the cosmic microwave background, we are not seeing a shell located at the edge of the universe in the ordinary sense. We are seeing light from very far away and very long ago, from the time when that distant matter released its radiation. Because light takes time to travel, looking far away means looking back in time. The background is the oldest light we can observe directly, coming from the surface of last scattering, which is the name scientists give to the moment when photons last scattered strongly before travelling freely. The phrase is technical, but the meaning is simple enough. It is the moment the universe became transparent enough for light to travel. This ancient light has been stretched during its journey. The stretching is not because the light got tired, but because space expanded. As space expands, the wavelength of radiation travelling through it stretches too. Longer wavelength means lower energy. Lower energy corresponds to a colder radiation temperature. This is why the cosmic microwave background is now microwave radiation, rather than the hotter glow it once was. The universe has stretched the light into coldness. That stretching also affects light from distant galaxies. Galaxies moving away with cosmic expansion have their light shifted toward longer wavelengths. This redshift is one of the main tools astronomers use to understand cosmic expansion. The cosmic microwave background is the grandest example of this cooling by expansion. It began as radiation from a hot young universe and now arrives as a cold microwave bath. The cold background helps set the context for the future as well. If the universe continues expanding for immense spans of time, radiation will continue to cool. Stars will eventually burn through their fuel. New star formation will decline as usable gas is locked away or dispersed. The universe of the far future would be darker and colder than the universe today. That future is far beyond human timescales, but it follows the same broad idea. Expansion and energy dispersal make the cosmic environment colder over time, while gravity creates local pockets of heat and structure. This does not mean the universe is simple or uniform in its cooling. Black holes, supernovae, colliding neutron stars, active galaxies and star-forming regions can be extraordinarily energetic. Some gas between galaxies and clusters can be extremely hot in terms of particle temperature. But because matter is thin and unevenly distributed, these hot regions do not make the whole universe warm in the everyday sense. The background remains cold. Local fires burn inside a vast old night. The cosmic microwave background also clarifies the difference between cold as a human sensation and cold as a cosmological condition. No person could simply stand in deep space and feel the microwave background as a breeze or chill. A person would need a spacecraft or suit to survive at all, but instruments can measure the radiation environment. They can show that deep space, away from local sources, is bathed in a faint glow with a very low temperature. That scientific cold is not about skin. It is about radiation balance. For an object in deep space, the background is what little warmth comes back from the universe. If the object is warmer than that background, it radiates more energy than it receives and cools. If it somehow became colder than the background, it would absorb slightly more energy than it emitted and warm back toward balance. This is the same broad idea as a room and a cup of tea, but the room is the universe, and the tea is anything alone in the dark. The room is extremely cold. This is why there is no contradiction in saying space is cold, even though radiation is everywhere. Radiation can be present and still correspond to a very low temperature. A whisper is still sound, but it does not shake the walls. The cosmic microwave background is still light, but it does not warm planets like sunlight. It is the cooled remnant of an earlier state, spread thin across the cosmos. The story also gives the darkness a kind of age. When you look between the stars, you're not looking at a simple blank. You're looking through regions where radiation from the early universe passes, where dust may drift, where faint gas may linger, where gravity has spent billions of years gathering matter into structures, and where the average background has cooled as space expanded. The cold is not just a lack of heat nearby. It is a result of the universe becoming large. That is one of the deepest answers to the original question. Stars are hot because gravity gathers matter into dense centers where energy can be produced. Space is cold because the universe is vast, expanded, and mostly empty, with its ancient radiation stretched into a faint microwave glow. Heat is concentrated in stars and other energetic places. Cold belongs to the enormous spaces between them, where little matter exists to store energy, and little radiation returns once warmth is emitted away. The cosmic microwave background does not make the universe feel cozy, but it does make it understandable. It tells us that the cold of space has a history. The universe was not always this way. It cooled into this state. The stars did not appear in an already familiar night. They emerged later, as gravity gathered matter in a universe that had become transparent enough for light to travel. Their heat shines against a background that remembers an earlier fire, now stretched into near silence. And that brings the discussion closer to practical survival. The ancient background sets the deep cold, but astronauts and spacecraft do not operate in a perfectly isolated universe. They move through sunlight and shadow, near planets and moons, surrounded by machinery that produces heat and surfaces that lose it. For them, the cold of space is not only a cosmological fact, it is an engineering problem, a life support problem, and a constant balancing act between freezing in darkness and overheating in the light. For astronauts and spacecraft, the cold of space is not a simple enemy. It is not like stepping outside without a coat, realizing the air is sharper than expected, and hurrying back indoors with your hands tucked into your sleeves. Space does not behave like winter air. It does not surround a person with a thick, cold substance that carries heat away in the familiar way. The danger is stranger and more demanding. In sunlight, an object can become too hot. In shadow, it can become too cold. Move between the two again and again, as spacecraft often do, and the challenge becomes less like surviving a freezer and more like balancing between a furnace and a deep, silent drain. This is why spacecraft are not simply built to keep heat in. They are built to control heat. That distinction matters. A winter coat is designed mostly to slow the loss of body warmth. A spacecraft must sometimes preserve warmth, sometimes reject warmth, sometimes spread warmth around, and sometimes block incoming radiation before it becomes a problem. It has to do all of this while travelling through vacuum, where there is no air outside to carry heat away, and no air outside to soften sudden changes. A spacecraft is a small island of managed temperature in a place that offers almost no help. Think about a satellite orbiting Earth. It moves through direct sunlight, then passes behind Earth into shadow, then returns to sunlight again. This can happen many times in a single day. While the satellite is lit by the sun, its outer surfaces absorb radiation. Some surfaces may warm quickly. Solar panels, antennas, instruments, and structural parts all respond according to their materials and coatings. Then, when the satellite enters Earth's shadow, that direct sunlight vanishes. The same surfaces begin radiating energy into space. The heating stops, the cooling begins, and the spacecraft must tolerate the swing. If it is not designed properly, parts can expand and contract too much. Electronics can drift outside safe limits, batteries can suffer, and instruments can lose precision. On Earth, we are protected from that kind of sharp thermal contrast by the atmosphere. Even when sunlight stops, warm air, ground, buildings, and water continue sharing heat. The planet does not forget the day instantly. In orbit, shadow can feel much more decisive because there is no thick external medium to carry warmth from lit regions into dark ones. A spacecraft can conduct heat through its own structure, but the vacuum outside will not do the mixing. If one side faces the sun and another faces deep space, those sides may try to become very different temperatures. The spacecraft itself must act as the bridge between them. This is one reason thermal engineers are so important in spaceflight. Their work is not always as dramatic in public imagination as rocket engines or landing systems, but without it, spacecraft would fail quietly and quickly. Electronics produce heat as they operate. Batteries have temperature ranges in which they work well. Fuel can freeze or overheat. Cameras and scientific instruments need stability. Human cabins need to remain within comfortable and safe conditions. A spacecraft is full of components that each prefer a certain thermal neighborhood, and space keeps trying to pull them into extremes. Inside a crewed spacecraft, the situation becomes more familiar but still unusual. There is air inside the cabin, so heat can move through that air. Astronauts breathe, computers run, lights operate, pumps move, and all of these produce waste heat. On Earth, warm air naturally rises because gravity makes less dense air buoyant. In orbit, where astronauts and cabin air are in continuous free fall, warm air does not rise in the same ordinary way. Without fans, warm pockets and carbon dioxide-rich pockets can linger around people and equipment. Air circulation must be forced. The cozy, breathable interior of a spacecraft is not a passive room. It is an engineered environment that must be stirred, filtered, cooled, warmed, and watched. Outside the spacecraft, the vacuum remains. Heat generated inside has to go somewhere. If it stayed trapped, the cabin and equipment would gradually become too warm. This surprises many people because space is described as cold, so it seems natural to assume cooling would be easy. But a vacuum is a poor place for dumping heat by the methods we use on the ground. There is no outside air to blow across a hot machine. There is no river or ocean to absorb waste heat. A spacecraft must move heat through its internal systems to radiators, and those radiators must release the energy as infrared radiation into space. In other words, the spacecraft has to glow its unwanted heat away in invisible light. Radiators are carefully placed and designed. They need a clear view of cold space. If they face the sun, they absorb heat while trying to get rid of it. If they face a warm planet, they may receive infrared radiation from below. If they are blocked by another part of the spacecraft, their ability to cool may be reduced. Their job sounds simple, but it depends on orientation, surface properties, mission design, and the changing environment along the orbit. A radiator is not just a metal panel, it is a planned exit route for heat. Spacecraft also use insulation, but not the same kind of insulation as a house wall or a thick blanket. A house is insulated largely to slow heat flow through solid materials and trapped air. A blanket keeps you warm because it traps air near your body and reduces the movement of that air. In space, outside the spacecraft, there is no air to trap. The main concern is radiation. This is why many spacecraft are wrapped in shiny multi-layer insulation. Those thin reflective layers reduce the exchange of radiant energy. They can help keep sunlight from overheating sensitive parts and help prevent internal heat from escaping too quickly. The familiar gold or silver appearance of spacecraft insulation is not decoration, it is thermal control made visible. The same balancing act applies to spacesuits. A spacesuit is often imagined as a kind of heavy protective outfit, but it is much more than clothing. It is a tiny spacecraft shaped around a human body. It must provide pressure, oxygen, carbon dioxide removal, temperature control, communication, mobility, and protection from micrometeoroids and radiation. The thermal problem alone is demanding. An astronaut working in sunlight can produce body heat through exertion, while also absorbing solar radiation. The suit must prevent overheating. In shadow, the astronaut may lose heat by radiation, and the suit must prevent dangerous cooling. The suit cannot simply be warm, it must regulate. During spacewalks, astronauts often wear a cooling garment beneath the outer suit. This garment circulates water through tubes close to the body, carrying away excess heat. That may sound odd in a place people think of as freezing, but physical work inside a sealed suit produces heat quickly. The astronaut is insulated, pressurized, and surrounded by equipment. Sweat cannot simply evaporate into open air the way it does during a jog on Earth. Heat must be collected and moved deliberately. The life support backpack handles that heat, along with breathing gases and other needs. In space, even sweating becomes an engineering problem. The outer layers of a spacesuit are designed to reflect sunlight, reduce heat exchange, and protect against the environment. White is commonly used because it reflects much of the incoming solar radiation and makes the astronaut easier to see against the darkness. The suit must handle direct sunlight, shadow, and reflected light from nearby surfaces. On the Moon, for example, an astronaut stands on a surface that can become very hot in sunlight, while the sky above remains black because there is no atmosphere to scatter sunlight into blue. The ground can reflect and radiate energy. The astronaut is not dealing with one temperature called space. They are dealing with a scene of surfaces and directions. The Moon is one of the clearest examples of why space thermal conditions are so different from Earth. Lunar daytime lasts a long time, and without a thick atmosphere or oceans, the surface heats strongly under sunlight. Lunar night also lasts a long time, and the surface can cool dramatically as it radiates energy away. In some permanently shadowed polar craters, temperatures can remain extremely low for long periods. These places are cold traps, where ice can persist because sunlight never reaches them directly. Step from a sunlit region into a shadowed one, and the thermal environment changes sharply. On Earth, air would blur that boundary. On the Moon, the boundary is much more severe. Astronauts on the Moon did not freeze instantly in shadow, or burn instantly in sunlight because their suits managed heat. The technology created a stable human environment inside the suit. It kept pressure around the body, supplied oxygen, and regulated temperature. The astronaut was not exposed directly to space in the way a bare object would be. Human survival depended on carrying a controlled pocket of Earth into an airless place. That is one of the recurring truths of space exploration. We do not adapt our bodies to vacuum. We bring an artificial environment with us. Spacecraft travelling closer to the Sun face a different version of the problem. The closer a spacecraft gets, the more intense the sunlight becomes. It may need heat shields, reflective surfaces, and careful orientation so that sensitive instruments remain in shade. A mission that studies the sun must survive the very radiation it is sent to observe. Its shield may become extremely hot on the sun-facing side, while instruments behind it remain at workable temperatures. This requires precise design. A small pointing error can expose parts that were never meant to receive direct solar heating. Near the sun, cold space is not the main danger on the lit side. Overheating is. Far from the sun, the problem changes. A spacecraft near the outer planets receives much weaker sunlight. Solar panels become less effective, and the environment offers little incoming warmth. Instruments and electronics may need heaters. Some missions use power sources that also provide heat, allowing them to operate in the dim outer solar system. The same vacuum surrounds them, but the balance of radiation is different because the sun is far away. Space is not one environment. It changes with distance from stars, with proximity to planets, with shadow, with internal heat, and with the shape and material of the spacecraft. A probe on Mars has yet another version of thermal struggle. Mars has an atmosphere, but it is very thin compared with Earth's. It can carry some heat and produce winds, but it does not moderate temperature as strongly as Earth's atmosphere does. A rover on Mars may face cold nights, dusty skies, and daytime sunlight that is weaker than on Earth. It needs heaters, insulation, and careful energy management. Dust on solar panels can reduce power. The ground can cool rapidly after sunset. The rover is not in open vacuum, but it is still in an environment where heat must be managed with care. On the International Space Station, thermal control is constant. The station is large, full of equipment and home to people. It receives sunlight, enters shadow, generates internal heat, and radiates heat away through large external radiators. The radiators are part of an active thermal system using circulating fluids to move heat from inside the station to the outside. The station must keep its crew comfortable and its systems reliable, while orbiting through repeated cycles of light and darkness. It is easy to look at images of the station and focus on its solar arrays and modules, but the thermal system is one of the reasons it can function as a living laboratory. Even small objects in space face thermal consequences. A tool, a bolt, or a camera can heat or cool depending on its exposure. A small dark object in sunlight may warm quickly. A shiny object may reflect more energy. A small object in shadow may lose heat quickly, because it has little stored thermal energy compared with its surface area. Surface area matters because radiation leaves from surfaces. A thin panel can change temperature faster than a large dense block. Shape becomes part of thermal behavior. Materials behave differently as temperatures change. Metals expand when heated and contract when cooled. Electronics can fail if components become too hot or too cold. Lubricants can thicken or evaporate. Seals can become brittle. Batteries can lose performance. Optical instruments can shift slightly as structures expand and contract, affecting focus and alignment. In space, temperature control is not only about comfort or survival, it is about precision. A telescope mirror, a spectrometer, or a guidance system may need stable temperatures to work properly. Small thermal changes can become large measurement problems. Some spacecraft intentionally use passive thermal control as much as possible. Passive means design itself manages heat without requiring much active power. Reflective surfaces, insulation, orientation, thermal coatings and radiator placement can all work passively. Active systems use heaters, pumps, louvers, circulating fluids, or other mechanisms. Most spacecraft use a mixture of both. Passive systems are valuable because they are simple and reliable. Active systems are valuable because they can respond to changing conditions. In spaceflight, reliability is not a luxury, it is survival. The battle between freezing and burning is therefore not a dramatic exaggeration. It is a practical daily condition for hardware and humans beyond Earth. In direct sunlight, radiation can deliver intense energy. In darkness, heat can escape into space with little returned. With no atmosphere to even out the extremes, everything depends on design. Spacecraft must decide in their structure where heat should go, where it should not go, what should be reflected, what should be absorbed, and what should be radiated away. This balance is also why astronauts do not experience space as a simple cold place, while safely inside their vehicles or suits. They experience the climate that engineers have created for them. The cabin has temperature and humidity. The suit has circulation and cooling. The spacecraft has heaters and radiators. The human environment is separated from the outside by layers of technology. Outside, sunlight and shadow remain severe. Inside, the goal is ordinary comfort, because ordinary comfort is what bodies need to think, work, sleep, repair, and stay alive. Sleep itself becomes part of the design. A crewed spacecraft cannot become too hot or too cold during rest periods. Fans must keep air moving. Carbon dioxide must be removed. Noise, light, and temperature all affect the ability to sleep. The human body still follows rhythm shaped by Earth, even while orbiting above it. Astronauts may see many sunrises and sunsets in a single Earth day, so lighting schedules and routines help maintain a sense of day and night. Thermal comfort is one part of keeping the body anchored in a place where natural cues are strange. There is something quietly impressive about this. A spacecraft is not only a machine crossing space, it is a negotiated agreement with physics. It accepts that vacuum will not carry heat like air. It accepts that radiation is directional. It accepts that the sun can overheat and shadow can chill. It accepts that humans are fragile, warm bodies built for pressure, air, and narrow temperature ranges. Then it answers with insulation, radiators, pumps, coatings, heaters, sensors, fans, and careful procedures. Spaceflight is not a conquest of nature in the simple sense. It is a long, detailed conversation with nature, where every overlooked detail can become serious. The same is true for future habitats on the Moon or Mars. A base on the Moon would need to survive long days and long nights, manage heat from sunlight, store energy, reject waste heat, and protect equipment from cold shadow. Some designs may use regolith, the loose lunar surface material, as shielding against radiation and temperature extremes. Buried or partially covered habitats could gain thermal stability. On Mars, habitats would deal with dust storms, thin air, cold nights, and limited sunlight. In both cases, the question is not only how to stay warm, it's how to control heat in an environment that does not behave like Earth. Even planets can be understood as natural thermal systems. Earth succeeds as a comfortable home because it has the right combination of sunlight, atmosphere, oceans, rotation, clouds, surface chemistry, and internal heat. It is not merely close to the sun. It processes solar energy in a complex way. A spacecraft must do something similar in miniature. It receives energy, stores some, rejects some, redistributes some, and protects its delicate interior from extremes. A spacesuit does the same around one person. Life beyond Earth depends on building small worlds that can manage heat. The human imagination often likes simple extremes. Space is cold, stars are hot, astronauts freeze, rockets burn. Reality is more interesting because the extremes overlap. A spacewalker can be in a place where the sun is dangerously bright and the background is deeply cold. A spacecraft can need cooling while surrounded by what we call cold space. A shaded instrument can need a heater, while a nearby sunlit panel needs protection from overheating. The contradiction disappears once we remember that heat travels by radiation in vacuum, and that temperature is about balance, not just location. This brings us back to the original wonder of the night sky. The blackness between stars is not warmed into comfort by all those distant suns because there is so little matter to hold and spread their energy. Yet any object that catches enough starlight can warm. A planet can become habitable. A moon's surface can bake. A spacecraft can overheat. A person in a suit can produce too much body heat and need cooling. Cold space and hot sunlight are not opposites separated by distance. They can exist side by side, divided only by shadow, surface, and direction. So the battle between freezing and burning is really the battle for balance. Too much energy in and systems overheat. Too much energy out and systems freeze. Too little circulation and warm pockets form. Too little insulation and cold creeps through radiative loss. Too little radiator area and waste heat builds. Too much exposure to sunlight and surfaces become unsafe. Every spacecraft must find a middle path through conditions that are not naturally gentle. That middle path is one of the reasons space exploration is so difficult and so beautiful. It requires us to understand not only grand ideas like stars, gravity, and cosmic expansion, but also the practical details of a panel facing the wrong way, a heater switching on, a cooling loop moving fluid, or a reflective layer preventing a delicate instrument from drifting beyond its limits. The universe may be vast, but survival often depends on small, careful acts of thermal housekeeping. And after all that engineering, after all the suits and radiators and reflective blankets, the view outside remains the same in its quiet way. A black sky, bright stars, harsh sunlight when the sun is in view, deep shadow when it is not. The darkness is not empty of meaning. It is the reason stars stand out so sharply, the reason spacecraft must be so carefully made, and the reason the cold of space makes the heat of stars feel even more remarkable as we turn toward the final part of the journey. And this is where the cold and darkness begin to feel less like a problem and more like part of the reason the sky is so striking. If space were warm in the way a room is warm, if it were filled with glowing matter in every direction, if starlight spread through it like heat through air, then the night sky would not look the way it does. The stars would not stand apart as sharp points. The Milky Way would not appear as a pale band across dark country skies. The planets would not shine like quiet beads of reflected sunlight. The darkness is not just empty background. It is the condition that lets the stars be seen. When we look up at night, we are seeing contrast. Our eyes notice bright points because they sit against blackness. A candle in daylight is easy to miss. The same candle in a dark room becomes the centre of attention. Stars are not small candles, of course. They are enormous spheres of hot plasma, many of them larger and brighter than our sun. But they are also very far away. By the time their light reaches us, it has spread across such large distances that only a tiny amount enters the eye. The darkness of space allows that tiny amount to matter. If the sky itself were glowing brightly, many stars would disappear from view, not because they stopped shining, but because the background would overwhelm them. This is why city lights hide the stars. The stars are still there above the street lamps, office windows, traffic signals, and glowing signs, but artificial light scatters in the atmosphere and raises the brightness of the night sky. The contrast is reduced. Fainter stars vanish first, then the Milky Way fades, and eventually only the brightest planets, the moon, and a few strong stars remain visible. Nothing has happened to the stars themselves. The problem is the background. A bright background steals the delicate difference between star and sky. Space, by contrast, gives stars a dark background because most of it contains too little matter to glow visibly. There are glowing gas clouds, dust illuminated by stars, auroras on planets, and many forms of radiation our eyes cannot see. The universe is not truly blank, but in visible light much of the space between stars is dark to human eyes. That darkness tells us that space is thin, that stars are separated by enormous distances, and that the universe has a history in which light travels through emptiness rather than filling a small closed room. There is an old question connected to this. If the universe contains so many stars, why is the night sky dark at all? At first, it seems that every line of sight should eventually end on the surface of a star. If space went on forever, if stars had existed forever, and if nothing changed, the sky might be expected to shine brightly in every direction, yet it does not. The night is dark because the universe is not an eternal static room filled evenly with stars. It has a finite age. Light travels at a finite speed. The universe expands. Stars are born and die. Galaxies are separated by growing distances. Light from very distant objects is stretched as the universe expands, shifting much of it out of the visible range. Some light has not had enough time to reach us. Some arrives weakened and shifted. The darkness is a clue that the universe has a beginning, a history, and a changing structure. So the dark sky is not a failure of the stars to do their job. It is evidence. It tells us that we live in an expanding universe where light has been travelling for only a limited amount of cosmic time. It tells us that stars are not evenly packed into every point of space. They gather into galaxies, clusters and filaments, with large regions between them where matter is sparse. It tells us that distance matters. Even the brightest star becomes faint when it's far enough away. The blackness between stars is not meaningless. It carries information about the scale and age of everything. The cold of space belongs to that same story. A warm, crowded universe would look different. A universe filled with dense glowing gas would scatter and absorb starlight. A universe with much more matter between stars would be less transparent. We would not see distant galaxies so clearly. The light from faraway objects might be blocked, blurred, or transformed before it reached us. The vacuum is harsh, but it is also transparent. It allows a photon leaving a star to travel for years, centuries, millions of years, or billions of years before meeting a telescope, an eye, a dust grain, or the surface of a planet. The cold darkness is part of what makes astronomy possible. When a star shines in that darkness, it is not merely a point of decoration. It is a physical signal. Its colour tells us about its temperature. Its brightness tells us about its power and distance, though those two have to be carefully separated. Its spectrum, the detailed spread of its light, tells us what elements are present, how fast it is moving, and sometimes whether it is surrounded by gas, dust, or planets. The dark space around it gives the measurement room to breathe. A star against darkness becomes readable. This is one reason telescopes are placed in dark locations, high mountains, deserts, and sometimes in space itself. Astronomers are not only looking for more magnification. They are looking for cleaner contrast, less atmospheric distortion, less moisture, less light pollution, and less thermal interference. Infrared telescopes often need to be kept very cold because warm instruments produce their own infrared glow. If the telescope is too warm, it can drown out the faint heat signals from distant dust, planets, and galaxies. To see the cold universe, the instrument must avoid becoming a bright source in the kind of light it is trying to detect. Even observation becomes a battle against unwanted warmth. That idea is very practical. A telescope looking for faint infrared light from a distant object must reduce its own heat emission. Otherwise, it is like trying to hear a whisper while standing next to a running engine. The distant signal may be real, but the local noise hides it. Space telescopes use shields, cooling systems, careful orbits, and reflective materials to keep instruments cold. The darkness and cold of space help, but only when the telescope is protected from the sun, Earth, and its own heat. The universe is observable because it is not uniformly bright, and our instruments must respect that. Human eyes work with contrast too. When you step outside from a lit room, the sky may seem almost empty. After several minutes, your eyes adapt. Your pupils widen. The light-sensitive cells in your retinas become more responsive. Fainter stars appear. The sky deepens. If the surroundings are truly dark, the Milky Way may become visible as a broad cloudy band. It is not a cloud in the atmosphere, but the combined light of countless distant stars in our own galaxy, mixed with dark lanes of dust that block visible light behind them. The view improves when the background grows darker and your eyes become more sensitive. Darkness is not only outside you. Your body must adjust to it. The stars feel wonderful, partly because they arrive through that adjustment. They ask for patience. A phone screen can ruin the view in a second. A porch light can flatten the sky. But if the lights are low and the air is clear, the stars return gradually. This is not only a pleasant experience, it is a small demonstration of how perception works. The universe is always sending light, but what we notice depends on the environment and on the instrument, whether that instrument is an eye, a camera, or a space telescope. The darkness also gives a direct sense of distance. During the day, the blue sky feels like a ceiling, even though we know it is not. The atmosphere scatters sunlight and fills our vision with brightness. At night, when the sun is below the horizon and the atmosphere above us no longer glows so strongly, the sky opens. We can see beyond the air into space. The blackness is not a surface, it is depth. The stars appear fixed on a dome only because they are so far away that our eyes cannot easily judge their distances. In reality, some are much closer than others, some are giant stars far away, some are smaller stars nearby, and many faint points seen through telescopes are not stars at all, but entire galaxies. That fact is worth sitting with in a calm, practical way. A tiny point of light may be a star in our neighbourhood of the galaxy. A faint smudge may be a galaxy containing hundreds of billions of stars. A patch of darkness may hide dust clouds where new stars are forming. A region that looks empty to the eye may be full of radio waves, infrared radiation, dark matter, sparse gas, or ancient microwave background radiation. Darkness in visible light does not mean nothing exists. It means our eyes are limited, and the universe is more varied than visible brightness alone can show. Still, visible darkness has emotional power because it lets the bright object stand out. The moon looks bright because the surrounding sky is dark. Venus can shine fiercely after sunset because the background has dimmed enough for its reflected sunlight to dominate. Jupiter and Saturn become steady points of pale light. A meteor becomes startling because it cuts across blackness. An aurora becomes vivid because charged particles make the upper atmosphere glow against a night sky. Contrast turns physical events into experiences we remember. The coldness of space adds to this in a more subtle way. Stars are not merely bright points on a dark ceiling. They are hot, active, energy-producing objects surrounded by vast regions that do not share their warmth. Each star is a concentration of matter and energy. Gravity gathers gas, pressure and temperature rise. Deep inside, nuclear processes release energy. That energy eventually escapes as light. Around the star there may be planets, dust, comets, magnetic fields, and winds of charged particles. Farther out, the radiation weakens, the matter thins, and the cold returns. A star is a local victory over cosmic cold, but not a permanent defeat of it. That makes stars feel more remarkable, not less. They are not heating an already warm universe. They are making warmth in a universe that mostly does not provide it. They create light from matter crushed by gravity. They make conditions that allow planets to receive energy. Around at least one star, that energy drives weather, oceans, photosynthesis, food chains, and minds capable of asking why space is cold. The darkness around stars makes their role clearer. They are not ordinary lamps in a room. They are engines of structure and change in a vast, thin cosmos. Our own sun is so familiar that it's easy to forget how extraordinary it is. We do not usually think about it as a star when it is warming our face through a window or drying laundry on a line. It becomes part of daily routine, the reason morning arrives and shadows move. But the sun is a star close enough for its radiation to become climate. Its light takes minutes to reach Earth, crosses the vacuum, enters the atmosphere, and is absorbed by the surface and air. That energy powers almost everything we experience as living weather. The other stars are suns too, but far away. The darkness between them and us is mostly distance. At night, when the sun is hidden by Earth itself, we see the wider family. The stars become visible not because they turn on, but because our local star is no longer flooding the sky. Daylight hides the universe by being too successful. The sun is so bright nearby that it fills the atmosphere with scattered light and overwhelms the faint signals from beyond. Night is what happens when Earth turns our part of the surface away from that glare. Darkness gives back the distant universe. This is a useful reminder that darkness is not always absence in a negative sense. In astronomy, darkness can be protection from glare. It can be the quiet condition needed for faint truth to appear. A detector needs darkness to measure weak light. An eye needs darkness to see faint stars. A planet needs night as part of its rhythm. Many living things depend on darkness for navigation, rest, feeding, reproduction, and migration. Artificial light at night can disrupt animals, insects, and even human sleep patterns. Darkness is not just what remains when light is gone. It is part of the natural environment. The universe itself contains many kinds of darkness. There is the darkness of empty space where little matter glows. There is the darkness of dust clouds, where visible light is blocked but infrared light can pass through more easily. There is the darkness around black holes, where gravity shapes the paths of light in extreme ways. There is the darkness of objects too cool to glow visibly, such as planets, brown dwarfs, and cold dust, which may still shine in infrared. There is the darkness of wavelengths our eyes cannot detect. Each kind of darkness has its own physics. Not all darkness is the same. The darkness between stars also makes motion and time more visible. A planet changes position against the background stars. The moon moves night by night. Constellations shift with the seasons. Meteors streak briefly and vanish. Comets appear, fade, and return on long schedules. The background is not truly fixed, but it is stable enough on human timescales to act as a reference. Ancient observers used that dark sky as a calendar, a compass, and a record of celestial order. The cold vacuum did not only preserve starlight, it helped make the sky useful. Before clocks, before satellites, before electrical lighting, the night sky was a practical tool. People watched the rising and setting of stars to track seasons. Sailors navigated by stars. Farmers connected sky patterns with changing weather and planting times. Mythologies grew around constellations, but beneath the stories were careful observations. The darkness allowed the stars to be seen, and seeing them helped human societies organize time, direction, and memory. The coldness of space is far away, but the darkness it creates has shaped human culture directly. Modern science has extended that old practice with instruments. We no longer only trace constellations, we measure stellar spectra, map galaxies, detect exoplanets, study supernova remnants, and measure the cosmic microwave background. Yet the basic act remains similar. We look into darkness and collect light. Every telescope is, in a sense, a patient device for catching what the dark has allowed to travel. The oldest light we can detect, the cosmic microwave background, is part of that same darkness even though our eyes cannot see it. It reminds us that the black sky is not empty of radiation. It is filled with a cold afterglow from the early universe. The stars shine in front of that ancient background. Galaxies cluster across it. Dust absorbs and re-emits light within it. The visible night sky is only one layer of a much richer radiation landscape. Darkness is what the human eye sees when the available light is too faint or too far outside its range. This makes the question of cold space even more interesting. Space is cold when measured by its faint background radiation and its lack of matter. But it is also full of light travelling between sources and absorbers. The universe is not cold because energy is absent. It is cold because energy is spread thinly across enormous distances, because matter is sparse, because radiation has cooled through expansion, and because stars occupy small regions compared with the vast volume between them. The darkness is the visible sign of that arrangement. The stars are the bright exceptions. There is a grounded comfort in that. The universe does not need to be uniformly warm to be full of activity. In fact, the differences make activity possible. Hot stars, cold clouds, warm planets, icy moons, glowing nebula, dark dust lanes, and faint background radiation all belong to the same physical story. Temperature differences drive processes. Energy flows from where it is concentrated to where it is less concentrated. Planets radiate into space. Stars shine into darkness. Dust warms and cools. Atmospheres circulate. Life uses energy from the sun before releasing it back as waste heat. The cold of space is not simply hostile, it is part of the flow. If everything were the same temperature, much of what we recognize as change would stop. Heat would not flow in useful ways. Stars could not stand out as sources. Planets would not have the same energy gradients that drive weather and chemistry. The universe is interesting because it is not even. It has concentrated heat and deep cold, bright centers and dark gaps, dense matter and thin vacuum. The night sky is a visible map of unevenness. That unevenness also makes habitable places rare and precious. Earth is not warm because space is warm. Earth is warm because it catches enough sunlight, has an atmosphere that helps regulate heat, has oceans that store and move energy, and rotates through day and night. It sits in a balance. Too close to the sun, and too much energy would arrive. Too far and too little. Too little atmosphere, and temperatures swing severely. Too much heat trapping, and the surface can become extreme. The cold, dark background of space makes Earth's balance more noticeable. Our comfort is not automatic, it is a planetary achievement. Stars, then, are wonderful, not only because they are bright, but because they create the possibility of warmth in a universe where warmth is not guaranteed. Around some stars, planets may orbit in regions where liquid water can exist under the right conditions. Around others, radiation may be too intense, or worlds may be too cold, too hot, too unstable, or too exposed. The search for life beyond Earth is partly a search for the right relationship between starlight and planetary matter. A star alone is not enough. A planet alone is not enough. The question is balance, atmosphere, chemistry, time, and protection. The darkness helps us search. When a planet passes in front of its star, the star dims by a tiny amount. Astronomers can measure that dimming and infer the planet's presence. When a planet pulls slightly on its star through gravity, the star's motion changes. When a young planet glows in infrared, a telescope may detect it if the glare of the star can be blocked. Each method depends on noticing small signals against a background. Darkness is not an obstacle only. It is also the contrast that makes discovery possible. Even the cold helps discovery. Cold telescopes can detect faint infrared signals. Cold space allows instruments shielded from sunlight to reduce thermal noise. Cold dust clouds emit radiation that tells us about star formation. Cold worlds in the outer solar system preserve ancient materials from the early days of planet formation. The chill is not only something to survive, it is something to study. So when we ask why space is cold when stars are hot, we end up with a richer answer than expected. Space is cold because it is mostly vacuum, because there is little matter to carry heat, because radiation travels until it is absorbed, because stars are far apart, because light spreads with distance, because the universe has expanded and cooled, and because the ancient background glow is now very faint. Stars are hot because gravity gathers matter into dense spheres where energy can be produced and released. The two facts belong together. The cold darkness is the setting that makes stellar heat visible, useful, and scientifically meaningful. And perhaps that is why a clear night sky can feel calming rather than merely empty. It shows us that the universe is not a single uniform blaze. It is structured. It has distances. It has quiet regions and active regions. It has old radiation and new stars. It has planets warmed by nearby suns and vast spaces where heat has almost nothing to hold on to. The stars do not erase the cold, but they punctuate it. They make islands of light in a sea that is mostly thin and dark. For a sleepy mind, that image does not need to be grand or dramatic. It can be simple. Above the roof, above the clouds if there are clouds tonight, above the atmosphere that holds your warmth close, space stretches outward. It is cold not like a winter wind, but like an absence of touch. The stars shine through it because there is so little to stop them. Their light travels patiently until some small part of it reaches a world, a telescope, a window, or an eye. The darkness makes room for that arrival. If you're listening somewhere warm, the warmth around you is local and precious. It comes from a heater, a blanket, a climate, a planet, and ultimately from a star close enough to matter. If you're listening somewhere cold, perhaps with your hands under a blanket or your feet searching for a better patch of warmth, that too is a reminder that heat is always a relationship. Your body makes it, your surroundings take it or return it, and the balance becomes comfort. Earth gives us that balance in ways space never would without technology. The next time you see a star, it may be worth remembering that its light crossed a darkness that did not become warm from the journey. It moved through vacuum, through cold, through distance, through time, until it reached you. That tiny point is not warming your skin, but it is carrying information from a hot place far away. It tells you that matter gathered there, that energy escaped, that space was transparent enough to let it pass, and that your eyes were ready to receive it. And now, as this quiet journey settles, we can return to the simple question with a calmer answer. Space is cold when stars are hot because stars are concentrated sources of energy, and space is the vast, thin distance between them. Heat needs matter or radiation exchange to be felt. The vacuum offers almost no matter. Radiation warms what absorbs it, not the emptiness it crosses. The universe began hot, expanded, cooled, and left behind a faint microwave glow. Against that old cold background, stars shine all the more clearly. So wherever you're listening from tonight, whether the room is warm, cool, silent, or softly lit, you're inside one of the rare comfortable pockets of the universe. Around you is air, pressure, matter, and warmth. Far above, the darkness remains, not empty of meaning, not empty of history, but open enough for starlight to travel. And in that contrast between a warm little world and a cold immense sky, the stars become not less mysterious, but more understandable and perhaps even more wonderful.